session in honor of Charles Pugh's 80+1 birthday. Charles, most of us know very well and love very well as well. He was born in 1940. He was a graduate student at Johns Hopkins and got his PhD under Phil Hartman officially, but also he worked closely with Mauricio Peixoto in Brazil on the closing lemma, which was the subject of his thesis, the C1 closing lemma. I think we're going to get some discussion in some of these problem sessions or some of these talks about the closing lemma. He was a professor at Berkeley forever, and many of us were students of his. He's had a total of 20, hold on, get out my math genealogy. Oh, shit. 20, Charles would know, 25 students and 70 descendants. So the number of descendants, that is students of students, has now really, well, that includes students, but nonetheless, the number of students has now eclipsed the number of students. And those of us who worked with Charles, I was his student in 1995, and several other of his students are going to speak today, know him as a amazing listener, very enthusiastic about math, kind, gentle, opinionated, and very playful. And I know that what I've aimed as an advisor to be like is Charles. And often I hear his voice in my head when I'm thinking about math problems. And well, I'm sure many of you have similar experiences. So we missed his 80th birthday. It happened during COVID and it just went right by. And I happened to notice it was his 81st birthday this year, and sort of started talking to some people about it. And Pablo Carrasco had the idea that we should really do something about it. And so we contacted Charles, and Charles said he would love to do something that didn't last too long and also just focused on problems, because that is something that Charles has always loved to talk about, is just interesting problems that he's thought about, other people have thought about for years, or maybe new problems. So that's how this conference is going. It's a problem session. And we followed Charles's wishes pretty much in who we invited, with a few surprises. And I think that's all we need to say. Do you want to add anything, Pablo?
I think that I'm going to say something at the end, so we don't go too much over time for Andy's talk, and then we can make something in the closing. So I'm going to show you, wishing him happy birthday, and then we'll say something more.
Hey.
Happy
Thank
birthday,
you very
Charles.
much. Thank you.
So Pablo, would you like to introduce Andy's talk?
Perfect, I will do that. Let me put everything here. Right. So what do I have to do? All right. There we go. All right. So, all right. Welcome everybody. And so we'll start with the actual talks now. And the first speaker is going to be Andy Hammerlindl from Monash University. He's going to tell us about the ergodicity and accessibility in dimension 3. Thank you, Andy.
All right, well, thank you, Pablo and Amy. It's a pleasure to be here, at least virtually. And I second all said about Charles as a supervisor. So I should get to it because we don't have a bunch of time and I want to go to bed fairly soon. It's midnight here. So I'll start with a problem or a theorem that Charles proved back in 1994. And the setting is consider a surface of constant negative curvature, so some higher genus surface. and you can look at the geodesic flow on the unit tangent bundle of that surface. So your surface is two-dimensional, so the unit tangent bundle is a compact three-manifold, and you have this geodesic flow defined on the unit tangent bundle. And there's a natural volume form, so that this is volume preserving. And what Grayson, Pugh, and Shub did was they looked at this flow. They took the time one map, so they got a diffeomorphism on the three-manifold, this volume preserving diffeomorphism. And they showed that that was stably ergodic as a diffeomorphism. And this was a big result when it came out, because up to that point, since the 1960s, basically, the only known examples of stably ergodic diffeomorphisms were Anosov diffeomorphisms. So this gave a new example of a stably ergodic diffeomorphism. And in the proof, there were sort of two key concepts going on in terms of why this was true. And the two key tools in the proof are partial hyperbolicity, and then a property for partially hyperbolic systems called accessible, or accessibility. And so briefly, I'm not sure what everyone's background is here, but I don't have time to go through the full definition of partial hyperbolicity. Basically, the idea is you have a diffeomorphism F on a manifold M to itself. That diffeo is partially hyperbolic if the tangent bundle splits into three subbundles. And the three subbundles are all invariant under the derivative, df. The unstable EU is expanding under the derivative. Vectors are expanding. The stable bundle, ES, is contracting under the derivative. And the center one is dominated. So there can be some expansion or contraction in the center direction, but not as much as the other bundles. And then if you're in the partially hyperbolic setting, you have these foliations, a stable foliation tangent to the stable bundle and an unstable foliation tangent to the unstable bundle. And then accessibility means the following property. So if you have a point X, for any 2 points, X and Y in the manifold, you can draw a path between these going along leaves in the stable and unstable manifold. So I didn't practice this part of my talk, but we'll see. Hopefully I can do this all right here live. So starting from X, you can go, along an unstable segment, and then a stable segment, and then an unstable segment, and a stable segment. And then after some finite number of steps like this, taking these paths, you can build this path that way going from X to Y. So what this time one map of the diffeo, if you perturb it, all of the perturbations are partially hyperbolic still, even though they're not time one maps of flows anymore. And they're all accessible. They have this accessibility property. And they use that to show the stable ergodicity. And so this was sort of this first result of using accessibility to show that certain partially hyperbolic systems were stably ergodic, and more came as time went on. And it led to Charles Pugh and Mike Shub conjecturing the following, which are now known as the Pugh-Shub conjectures. So in this setting, they have volume-preserving, partially hyperbolic CR diffeos. And the way they originally stated it, they had R greater than or equal to 2, and that's what I'm going to do in this talk here. And they stated three separate conjectures. So the first one is that this accessibility property is open and dense among all these diffeomorphisms. The second one is that accessibility implies ergodicity. So if you have an accessible volume-preserving system like this, then it's ergodic. And then the third conjecture is that ergodicity is this open and dense property among these things. Or maybe I should be careful and say stable ergodicity.
Yes.
Oh, someone said yes. I don't even know who, but yes. So, and if 1 and 2 are true, you can see that 1 and 2 together give you this mechanism to prove 3. But it is possible that maybe 3 is true, but 1 and 2 aren't true. That maybe ergodicity, stable ergodicity, is this open and dense property among these systems, but the accessibility, at least accessibility on its own, isn't the mechanism for that. And so far as I know, in their full generality, these conjectures are all open still. So if you know differently, feel free to jump in. That said, the conjectures have been proved in a lot of specific settings. So adding in additional assumptions here. And so I tried to, in this slide, sort of give a list of like all of the people that have proved some version or variation of the Pugh-Shub conjectures in some setting. And I'm sure I've screwed up. I'm sure I've missed people. So if you've proved some version of the Pugh-Shub conjectures and I missed your name, then feel free to like shoot me an angry email. And the next time I give a talk like this, I'll be sure to include your name. But it also shows sort of this value of stating a good conjecture. And in some ways, a good conjecture can lead to a bunch of interesting research. And with the Pugh-Shub conjectures, that's definitely the case. So for the rest of the talk, I'm going to talk about partially hyperbolic systems in dimension 3 and the consequences of the Pugh-Shub conjectures there. And in that setting, the center is one-dimensional. And the Pugh-Shub conjectures have been verified there, where the center is one-dimensional. So for the rest of and so in this setting, we know that the typical system is accessible and it's ergodic in this setting. And so in fact, like open and dense, we have these accessible ergodic systems. And so to me, an interesting question to ask in this setting is, what are the exceptional cases? What is this meager set of non-accessible or non-ergodic systems? And can we take this set and can we give some sort of classification? Can we determine exactly what these systems are? What are all the non-ergodic ones? And in general, for all three manifolds, that's still an open problem. But there has been a lot of work on this, and it has been answered in a lot of settings. So I'll talk about what is known in this setting in this question here. And I'll spend most of my time talking about the three torus for a couple reasons. One is it's sort of in some sense, it's the simplest manifold that supports partially hyperbolic systems. And it's sort of easy to understand what the three torus is. And yet, surprisingly, it's sort of the most complicated in terms of whether things are ergodic or non-ergodic, accessible, non-accessible. It's sort of a complicated and interesting thing what happens in the three torus here. And the other reason is it ties into the work I did doing my PhD at the University of Toronto with Charles. And so Charles Pugh was in Toronto for about a 5-year period or so, which fortunately, like more or less exactly coincided with the time I was doing my PhD studies there. And it was fantastic to have him as a supervisor there. So I remember, we had regularly scheduled meetings once a week, but often his door was open and just, several times a week I'd just come by and I'd be working on this and have some ideas and have some questions. And almost always he was, perfectly available and had the time. I would drop in and we'd talk, sometimes for hours just about all of these things. And as Amy said, he was always very excited and helpful and just an absolute wealth of knowledge in all of these things. So the thesis couldn't have been done without him, certainly. And he was, an integral part in doing this. And so what was the result? The result in the end for my PhD thesis was this thing about classifying partially hyperbolic systems on the three torus up to leaf conjugacy. And so the result was any absolutely partially hyperbolic diffeo on the three torus is leaf conjugate to a linear system. And I won't explain, I mean, I didn't really define partial hyperbolicity. I certainly won't talk about what absolute means. But later, when I was working with Raphael Potrier, we were able to show, we don't need absolute partial hyperbolicity. The same result holds if we're in the volume preserving setting. So this result of classification up to leaf conjugacy, if we're looking at these volume preserving maps.
What is leaf conjugacy?
Oh wait, what's that? Sorry?
What's leaf conjugacy?
Oh, I'm not going to define it either. This is a 25-minute talk, so I don't define anything. I just talk and talk. But I will say on the next slide here, I will give sort of the upshot without giving the definition. This is more or less colloquially what the what the consequence of classifying these things up to leaf conjugacy is. Basically, what you get are two types of partially hyperbolic systems on the 3 torus. So the first one that I've shown on the left here is a skew product, or what I'll call a topological skew product. And in this setting, you have a center foliation. You have this foliation tangent to the center direction. And here, all of the leaves of the foliation are lines. So they don't have to, if the system's linear, then you'd have these perfectly vertical lines, but we can have perturbations of that in other ones. So in general, it's this topological, C0 foliation with C1 leaves that are these center circles. And the other type of partially hyperbolic system on the 3 torus is what are called derived from anosov systems. And these are partially hyperbolic systems that are homotopic to anosov systems on the 3 torus. And there you have a minimal center foliation. So all of your center leaves are lines. They're like immersed copies of the real line. And because it's minimal, all of the center leaves are dense. So we have these two types of systems. I'll talk about the skew products first and then the derived from anosov systems. So if we're looking at these skew products on T3, what are the known non-accessible examples? And if we have more time, or if this was like a classroom where I do like active learning and pause for a minute or two and let everyone sort of brainstorm and think, but there's no time. So here are the examples. The first one is, instead of doing a skew product, I'll just do a direct product. So I'll take the cat map on T2, and I'll direct product that with just the identity map on S1. And so I can imagine my coordinates are sort of X, Y, Z here. So my cat map is acting on X and Y, and then nothing's happening on Z. It's just the identity map there. And so if you look at sets of this form, the 2 torus, T2, times some constant value Z, those are going to be invariant under this dynamics. And you can show that the stable and the unstable directions are tangent to this 2-dimensional torus that's embedded inside of the 3 torus. So you have this invariant set, and it's saturated by stable and unstable leaves. And if you're trying to travel along the stable and unstable leaves, you can never leave this submanifold, this region T2 times Z. So this is, I didn't define it, but this is an accessibility class. And so a system is accessible if and only if it has a single accessibility class. And in this example, it's not accessible. And for every value of Z, we have all of these different accessibility classes. The system is not ergodic. We have lots of invariant sets of intermediate measure. All right, so example 2 is a slightly more complicated, a variation on this theme. So I'll do a direct product again. I'll do the cat map times the rotation, and I'll do an irrational rotation on this circle. So the accessibility classes here, again, are the same. We have the stable and unstable directions inside of these horizontal 2-dimensional tori embedded in T3. But now the system is moving them around. We have this irrational rotation in the Z coordinate, so these things are moving through. And if you go back and remember your introductory ergodic theory courses, if you have a mixing map times an ergodic map, then the result is ergodic. And the cat map is mixing. So this system is ergodic, but it's not stably ergodic. If you just adjust your angle slightly, this theta, you can move it between rational and irrational values. So it's not an ergodic map. And it's not, what am I saying? It's not stably ergodic. And also the 3D system is not mixing. So the Pugh conjecture, when it's been proved, usually the results show that the resulting system, not only is it ergodic, it's mixing. And in this setting, we have something that's ergodic, but not mixing. And the final example I'll give is, I'm going to do a perturbation. So if I go back to example 1, the anosov map times the identity map, if I start with that, I can just start perturbing this system and sort of making bigger accessibility classes. So one way to do this is take S1, which I've sort of drawn as this vertical line here. You imagine this bottom point and top point are identified here. And then I take some open subset of S1. So I have an open subset of the circle. It's some collection of intervals. And on each of those intervals I can do this perturbation method. There's this way improving the version of the Pugh-Shub conjectures in center dimension 1. Rodriguez, Hertz, and Erez gave this idea of how you can, perturb a system to sort of break open these accessibility classes. So there's a way in each of these things, T2 times I, to do some small perturbation of your system to build this, make this into an accessibility class. So we can make a system like this that's not ergodic, but it has a bunch of different accessibility classes. So for each I, we have this open accessibility class, T2 times I. And for all of the points sort of Z that are not in, if I have a point Z that's in the circle, but not in U, I guess, then I still have this compact accessibility class, a copy of the 2 torus and horizontal torus there. So those are three non-ergodic, three non-accessible examples in this skew product case. And in 2017, I proved a theorem that basically said this is more or less it for. So here's the theorem in all the gory detail. If you have a diffeomorphism F on the 3 torus, that's a C2 volume preserving topological skew product, then one of the following 3 cases hold. The first case is that F is accessible and it's stably ergodic. So again, from the Pugh-Shub conjectures, this is the open and dense behavior. Most of the diffeomorphisms are going to be in this accessible, stably ergodic setting. The second case is more or less my example 2. You have that the system is topologically conjugate to an Anosov system like the cat map times a rigid rotation. And you can even say more here. You can say exactly what the ergodic components are, what the accessibility classes are, and so on. And then the last case is more or less what the example 3 was. So there's some map from T3 down onto the circle, this map P, the C1 surjection. And then you can sort of look at some open set U inside of the circle, and using this open set U, you can sort of realize all of the accessibility classes of the system on T3, either as these open accessibility classes like this T2 times I that I had before, or a copy of the 2 torus, T2. All right, so that's more or less everything I wanted to say for the skew products. And what is it? So this assumption I put in volume preserving here. There's also interesting things that you can do with accessibility outside of the volume preserving setting. And I'll just mention briefly that a very similar theorem holds even in the non-volume preserving setting for these types of skew products, but it's a little more complicated. All right, so that leaves the other half of these systems on the 3 torus, these derived from Anosov systems, where you have a partially hyperbolic map homotopic to an Anosov map. And when I was finishing my PhD work with Charles, I was finishing up these results with leaf conjugacy. I was sort of thinking, what is the value of this? What's the value of knowing what these systems are up to leaf conjugacy? And this particular question, right? Can you show, using this classification up to leaf conjugacy, can you show properties such as accessibility and ergodicity? And for these derived from Anosov systems, like I strongly suspected that you should be able to use this to prove that all of these systems are ergodic in the volume preserving setting. And shortly after finishing my PhD in 2009, I went to the Beyond Uniform Hyperbolicity conference in Beijing, which was fantastic. And I met Hannah and Raoul there, and Raoul Erez and I started working on this problem together. And we proved the following version of the theorem here. So imagine you have F of volume preserving partially system on the 3 torus. And suppose that it's homotopic now to a linear Anosov diffeo, which I've written capital A here. So this is derived from Anosov setting. Then we have two possibilities here. So either F is accessible, and therefore it's ergodic because the Pugh-Shub conjectures hold in this setting, And again, that's the default, open and dense kind of setting. Or if it's not accessible, then we get this very interesting topological conjugacy H between F and the linear anosov map A. So this is a topological conjugacy, but not only that, it sort of maps all of the foliations of one system to all of the foliations of the other system. So this anosov diffeomorphism in this setting, you can also view it as partially hyperbolic with this three-way splitting into the stable, center, and unstable directions. And this topological conjugacy of H maps all of the stable leaves of one system to all the stable leaves of the other system, and the same for the center and the unstable. So in some sense, up to this C0 map H, we have the complete picture of how F looks like. We have all of the foliations, and we know exactly what they look like. They look exactly like an anosov map, and Raoul and I strongly suspected that this thing, if this happens, it has to be anosov, but we weren't quite able to do this. So we proved this thing here, just as it is stated. And we couldn't get ergodicity either, because we didn't know if H was absolutely continuous, right? If H is absolutely continuous, then a property like ergodicity will carry through the topological conjugacy. But we couldn't prove that, so we didn't get a definitive answer for ergodicity. But then Shub and Shi worked on this problem, and they had some interesting ideas of looking at sort of distances along these leaves, and they managed to go through it, and with quite some new insights on the problem, they were able to actually prove this thing. So in the case 2 that from the previous slide with my theorem with Raoul, they showed that in that case, in fact, that system is anosov. F itself is not just topologically conjugate to anosov, it is anosov. And so the result is for these derived from anosov systems, volume preserving derived from anosov systems on T3, either they're accessible and therefore they're ergodic, or they're legitimately an anosov system. And so in that case, they're also ergodic because they're a volume preserving anosov system. So in the volume preserving setting, that proved things. And then shortly after they proved that, I visited Shi in Beijing, and we worked on this problem in the non-volume preserving setting. And so we were able to prove the same thing as well in the non-volume preserving setting. So either these sort of derived from anosov systems, either they are accessible or I have, this slide. I knew I wasn't going to get time for this, but there's been a number of results by a number of people in other settings. So this is the very jot form version of all sorts of results about accessibility in other three manifolds and what we know. And we have, in some settings, we have, again, a very good picture. And yes, if you're curious, maybe send me an email or something. I don't think we have time to go through these in detail. And then finally, I want to close again to thank Charles for all of his help, before, during, and after my PhD work. He's been fantastic in all of that, and it's been a great experience, and it's been wonderful to work with him. And happy birthday as well, Charles. All right, I'll stop there. Thank you.
Thank you very much, Andy.
Thank you, Andy. Does anybody have any questions for Andy?
I can't see the chat. I don't know if there's any chat questions.
There's no chat questions.
Not really, no.
So what, from all of this kind of work, what is your most burning question that you would love to see answered related?
Well, I do think if I had to guess on this, and there's a conjecture by Rodriguez, Perez as well on this, that sort of all of the non-accessible systems in dimension 3 are known. So their conjecture is if you have a if you have a non-accessible system in dimension 3, then it has to have a US torus, like this 2 torus, this accessibility class that's a 2 torus. And we know if it has a 2 torus, again, from their work, that it's on certain manifolds, and then basically all of the accessibility classes have been classified there. And I'm certainly, I suspect that is true. I suspect that everything else is accessible basically in this 3-dimensional setting. And I think that's not, I don't know, that's not like an insanely hard problem. I think there's a good chance that we could actually answer that definitively. So I guess in here, that's sort of the burning question on this one.
So you always have, for volume preserving, you always have stable ergodicity, or you always have ergodicity, unless you have one of these SU toruses.
Yeah.
Any comments on the question, or does anyone want to follow up? Hannah, I see your face, so I was wondering if you might.
No, I that is also a burning question for me.
All right.
Any other?
Since Pablo and I don't know who's Pablo, to you, back to you.
No, I was just saying let's thank Andy again. And then probably you can introduce the next speaker, and we'll have one each other. Do you think that's right? Perfect.
Okay, Lan,
Yeah.
do you have? Are you going to talk with slides or just talk?
Yeah.
It up?
Charles, do you know that my younger son is in California now? He's in UC Davis.
Oh, no, I didn't know that. Oh, cool.
You knew him, Andres, the one who was
Of
here.
course.
He started
Yes.
today. He's starting classes today.
And what will be his subject of interest?
Mathematics.
Okay, well, I hope to see him sometime. Cool.
Yeah.
Congratulations, Hannah.
Thank you.
Do I share my screen correct?
Yes.
Okay, good.
So I guess we can start. We advertised that the next talk would be at 35 after. So, although if we're ahead of time, maybe that's a good thing. But actually, I do need to take a 2-second break. So just 1 sec.
Professor Lan, maybe you can zoom your screen, or you put it in full screen.
What?
Maybe you can put your slides in full screen. I think it is the red
Oh, no,
arrow
no.
which is below. The red arrow, you see it? There is a red button there. I think that works. Just in the below the screen, in the top, almost top right corner.
No. This is not. Oh, here
There is
it seems to be
there is an eye,
the whole screen.
right and then there is an arrow. Just lower your mouse.
What? Sorry.
Yeah, go to your mouse.
The bottom.
Just next to the there is an eye below, and
Oh,
then there is a
my
red
camera?
arrow. Maybe I think it is that one. There are those buttons.
There's some problem with my camera,
Ah,
I think. So I do not see my picture very well.
I see.
Can you see the screen?
Yes.
It's okay.
We can see the screen, so you can't share.
Okay.
You can't do full screen for this.
Oh.
You don't have to do full screen if you don't want to, especially if you can't see the screen.
Isn't there some command something F or something L that makes it full screen?
I think it is the red button below.
Yeah, there's
Yeah.
Command L works, but it works with Acrobat Reader. This is not Acrobat
That's
Reader.
WPS. Yeah.
No, but the red button below, that one is full screen.
Okay, I think we'll just stick
Yes.
with this format. I think everyone can see
It's
it.
okay.
All right.
Yeah, it's
so
okay.
It's my pleasure to introduce Lan Wen, who's in the second latest time zone here. And we really appreciate your staying up to do this. Go ahead. From Peking University, we have Lan.
Thank you, Amy and Pablo, for the organization. And I'm going to recall some present moment I had the opportunity to have with Charles Pugh. I put all this in a PowerPoint. I met Charlie at IBM Watson Research Center in the winter 1989. Some days earlier, Charles Stresser happened to be in the audience when I was giving a talk about the C1 closing lemma for non-singular endomorphisms at the Midwest Dynamical Systems Conference held at Northwestern University. He would like to invite me to their center for a short visit. He said Charles Pugh is visiting their center and he might be interested in this result. Some days later, Charles Stresser called me telling his arrangement for my visit and explained how to get their place. He said Charles Pugh would like to talk to me. I was very excited. Charles Pugh is the person I have long been looking forward to meeting because his famous work on the C1 closing lemma. When I stepped in Charlie's office, I noticed a paper on his desk that looked familiar to me. He told me that this is my paper on the C1 closing lemma for non-singular endomorphisms submitted to the ergodic theory in dynamical systems, and he's referring. I said, I've just had my paper retyped by a technician in Peking University Press with some new technology. LaTeX seems not yet available at the time, which is much prettier than the old one typed by myself with an old-fashioned typewriter. He asked me if the two versions are different mathematically. I said no. He said then he would prefer the old one because he has been familiar with it. I was a little bit disappointed, but I think Charlie was right. Looking pretty or not is not important in mathematics. In the following days, we had intensive discussions on the subject. Charlie is very careful, very rigorous. People usually like to listen to the ideas, but not the details. Charlie does not. He pays attention to the details as well. I like it. To be challenged by him is an exciting experience. Mike Shub was away those days, so I didn't meet him. Charles Stresser is also named Charles. I had difficulty to manage the situation. Charlie then told me that Charles can also be called Charlie, a way to call a friend. I asked, who should I call Charlie? Charlie said, me. I have been always calling him Charlie since then. In summer 1996, we held the Dynamical Systems Conference in Beijing. Many people came. Many came to China for the first time. At that time, China was quite behind in facilities. The lecture room has only one air conditioner at the corner near the front door. It does not help much, and everybody got wet. You can imagine how exciting and crowded it was to have participants like Steve Smell, Mike Shub, Jaco Palace, Maria Pacifico, Wellington de Mello, Marcelo Diana, Bob Williams, Clark Robinson, John Franks, Anatoly Katov, Lai Song Yang, Tianyan Li, Jim York, Louis Block, Kenichi Shiraiwa, Shuhei Hayashi, Kazuhiro Sakai, and a number of China-origin young stars in the US, like Jeff Shub, Conan Wu. We never had something like that again. Among all these remarkable participants was Charlie, too. I give a talk on the Sylvain connecting them joined with Jeff Shub. Charlie was interested in it. He got a cold, but he decided to leave 2 days later than his schedule so that we could have more time to talk. The next day, the conference was over. In summertime, the campus was quiet. Charlie and I met in a small classroom. I brought a small bottle of Chinese medicine for him, one with suspicious dark color. He didn't ask anything, but took the bottle and swallowed the whole bottle of the medicine. We had intensive discussions with details as before, but the deepest image kept in my mind for that day, without medicine. The closing lemma problem asks, here I just talking about something very naive, whether a reality by a small perturbation of the system. Steve Smell told many times a story about it. At first glance, the problem looked easy, and Rene Tom did tell Smell so. The natural design for the perturbation could be like this. Take a small ball B around the non-wandering point. Then there is a point X in B, and an integer n such that the nth iterate of X, which is Y, is also in B. We may assume that Y is the first return, so that all the intermediate iterates are outside B. Take a diffeomorphism H such that H is identity outside B, and it takes Y right onto X. Then we define the new map G to be the H composed with X. Then the G to the end of X is X. As the picture. Here's the small ball around that non-wandering point, and here's a point X that comes back for the first time as Y. Then we define a homeomorphism H is identity outside of this little ball. So in particular, if Fx is composed with H, will be the same because H here is identity. So the F equals F. Now F equals G equals G equals G equals C. But only here, this is F, but and here the H does something for the first time. It takes Y to X. So the X becomes periodic to G. This perturbation will be C0 small. That is, G will be C0 close if H is C0 close to the identity. It suffices if the ball B is small. This is guaranteed because for any small neighborhood B of the non-wandering point, there are always such 2 points X and Y, that the C0 closing lemma is indeed in C. However, the perturbation is not C1 small. To be C1 small, not only the ball B should be small, but also the 2 points X and Y should not be like 2 antipodal points near the boundary, because that would yield a large expansion of distance, as points on the boundary are fixed. In fact, X and Y should be the center of B, say in epsilon B, the epsilon kernel of B, like this picture. This is a small ball, and the map is identified outside and on the boundary. So if X and Y are like that, then taking Y to X will expand the distance of a very large. No matter how the ball is small, it doesn't matter, but the expansions could be arbitrarily large. So for the C1 to be C1 small, this 2 point has to be near the center. So we say this 2 point has to be in the epsilon kernel of this small ball. Thus, both X and Y should be near the center. But this is not guaranteed, because Y is the first return of X to B. And there is no reason why the first return must hit B near the center. Thus, the C0 proof fails for the C1 case. Tom told Smell later that to think of the closing lemma easy is the biggest mistake he made in his mathematical career. It was Charles Pugh who solved this hard problem for the C1 quality. Yeah, as Amy just said, it is indeed in thesis. Very roughly, his strategy is like this. Instead of a single push, he uses a long sequence of epsilon kernel pushes, like the picture. Then for the close, after the long sequence of pushes, then you pick some original orbit to get it close. So the picture looks easy. The design looks simple because the picture treats the map naively like a translation. Say to the minimum, the picture does not display the possible distortions caused by the iteries of the map. It is not clear if bad distortions would cancel out the efforts of the pushes. In fact, the C1 closing lemma of Charles Pugh is an extremely hard fail. 54 years after, today we are still in the C1 category. The C2 closing lemma seems out of reach. At the turning of the century, Steve Smale raised 18 problems in his paper, Mathematical Problems for the Next Century. The CR closing lemma is the 10th. The journey towards the closing lemma started with Charles Pugh is very charming and has deeply stimulated people's enthusiasm. Among many others are our colleagues and students. Our people study very hard the relevant techniques and get kind of familiar with it. Recently, Shub and Yi proved the CR closing lemma for partially hyperbolic diffeomorphisms of one-dimensional center, reflecting the persistent dream of our people about the closing lemma. Let me also tell an elder colleague, Mike. Around the summer 1988, one day I happened to notice in the library a paper in Chinese by Jie Hua Mai that gives a geometrical proof for the C1 closing lemma using elixirs. I couldn't believe my eyes, because the closing lemma was to me far beyond my head. It was this paper that brought me into this beautiful field. My teachers in a university in the south, far away from Beijing. He was a student of Peking U a few years ahead of me, so that we did not know each other at that time. He is extremely strong in mathematics, but somehow weak in speaking English. He told me that he has a valuable photo with Charlie taken at the 1996 Beijing conference, but now the photo is in his old home in Shantou, another city, so that he cannot share the photo with us today. He has me say for him, "Happy birthday to Charlie." I cannot give a even brief survey for the recent book of Charles Pugh, but I wish to say we are very grateful for a book of him with Maurice Hirsch and Mike Shub. This is the book Invariant Manifold. Everybody knows this book. It is certainly one of the most popular books in dynamical systems. Yeah, this book. It is a hard book, but very beneficial for our people. It serves then as the main reference for our graduate seminar. We have a weekly seminar for our faculties and graduate students. Usually, we have our students give talks in the seminar about various topics. Materials from this book, the Hirsch Group 2, are often picked up as subjects for the seminar. I remember once a student talked about the CR section theorem of the book. It was really hard to us, and it took quite several weeks. But we did learn a lot from it. And our students are found quickly more mature through such studies. It means the book is very to build a solid basis of knowledge for dynamical systems. I wish to share also an experience in my teaching. I taught dynamical systems course many times in Peking U. One topic I like very much to teach is Charlie's proof for the Hartman-Grove theorem. There are a number of different proofs for this result, but I found Charlie's proof particularly simple and elegant, so that it can be put very early in the course, about the fourth week of the semester. We have 16 weeks in one semester. The topological conjugacy we are looking for is written as identity plus eta, where eta is the continuous map with small subgroup. This is a good design of study. To find the conjugacy, then reduces to find the fixed point eta by the contraction mapping principle in the subform. That is easy to estimate. Charlie has many big results of research, but I also like such elegant presentations of well-known materials by him. His presentations, as well as his talking, are clear and clean. That is his style. I have always included this proof of Hartman-Grove theorem by Charlie into my lecture notes for teaching. Later, the lecture notes become a book in Chinese. Our first year graduate courses are taught in Chinese. And this proof is printed there. You can see his name is among the Chinese characters. As a first year graduate course, the lecture notes do not mark the names of the authors for various results. This is an exception in my book. Yeah, you can see this is let's see. can see here. In this Chinese character, you can see a Chinese name here. This is an exception. The next picture is the page taken from a paper by Jeff Shaw and me about the existence of this sequence of hexachronal pushes. We put a remark there to thank the referee. The referee pointed out that a point in our paper needs to be fixed and suggested how to fix it. He suggests to insert another parameter beforehand to make room for a final translation of the whole sequence of hexachronal pushes. The suggestion is very to the point. The referee also wrote that he will see the revised version and the paper can be accepted directly. Jeff and I guessed that the referee was Charles Pugh. Yeah, this is that page. We wrote here, we thank the referee for pointing out to us. This is my talk. Happy birthday, Charlie. Yeah.
Thank you so much, Lan.
Lan Wen, thank you very much. Sweet of you.
You're welcome, Charlie. I can't believe that it's 80 years already.
But you too are experiencing this phenomenon.
Yeah, this confession is everybody's old.
Charles, were you the referee?
Is there
You can always say you don't remember.
I wanted to just make a quick comment related to Lan's beautiful talk. At one point I was talking, of course, the stimulation for Charles' thesis was Mauricio Peixoto, who was studying the, vector fields on surfaces. And we were talking about that one day, Mauricio and I, and he said, I was at Princeton in the late 50s, and not many people were really interested in what I was doing. But I happened to have a conversation with Hassler Whitney one time about what I was doing, and I mentioned to him the closing lemma, and Whitney turned to me and just said, that's trivial in C0, but it's not so trivial in C1. And according to Mauricio, Whitney was the first who pointed out the difficulty about doing that theorem in C1.
That sounds like the kind of thing Whitney would know a lot about.
Absolutely.
Are there any comments or questions?
Well, I have a question.
I'll make one comment. Sorry.
Comment away.
Folkert was started, so.
Well, so my question is, it seems to be that if you add an additional condition, for example, area preserving or symplectic or something like that, you have a different conversation as far as these closing lemmas. Is that your impression also, or?
Not exactly.
This has been done in the paper of Charles in the flat province.
Okay. So there are
mostly it's the same.
There are these papers by these the Japanese people who sort of have some, C infinite closing lemma and whatnot, but that's all under these sort of symplectic preserving condition. So I wonder if this is something that makes sense to you.
With respect to the C infinity, or
yes, for example,
closing lemma, as opposed to the C1. The C1, it's very similar in the symplectic setting, but yeah, there are definitely techniques in symplectic.
Yeah, right. And so
topology, the work of Asaoka and others.
Yeah, exactly that. It's that. So we're looking a little bit into it at times, whether or not you can make it a real analytic. It may be possible. So to me, this is sort of like another avenue, something that people could look into as far as closing lemma, so you have something extra like a Hamiltonian system or something like that. So this is, I think, more, application areas of the sort of ideas. So anyway, this is my comment.
I think that the Hamiltonian is
Yesterday
a
was a
example,
top.
no?
Okay, wait, we might have to raise hands.
Oh, sorry.
Because, well, Charles was going to make a comment. So, Charles, you were about to say something.
Yeah, the simplest unsolved C2 closing lemma is on non-orientable surfaces for flows. A couple of simple non-orientable surfaces, it's known. But in general, even in that two-dimensional case, it's an open question.
For flows.
This is more recent. Flows in dimension 2
right.
on sort of multi-handled but non-orientable surfaces.
Yeah, I wanted, Charles, on that. I know about Gutierrez's result on the surface of genus 2. Is that it?
Yeah.
Okay.
I believe it may be one handle more, but that's it. Essentially, and I've forgotten who's done what, but how about that, though? Surfaces.
That is amazing. Enrique, because you raised your hand. Everyone needs to raise their hands from now on. Enrique.
Oh.
Hi, Charles. Great to see you, and thank you, Lan Wen, for the lovely talk. And the only comment is yesterday was a talk by Hutchinson in a conference about symplectic dynamics, and he was announcing a C-infinitive closing lemma for the torus. And it's related, yes, so it was related to the strategy developed by Erie, that he realized how all the symplectic capacities, and in particular the one built on floor homologies, floor periodic homologies, would help in a way to solve the closing lemma. So there are many, let's say, no dynamic.
Enrique, area per Serving case or area per Serving case or any case?
Yes, it's a volume preserving case.
Volume per Serving.
It's kind of intriguing and really two-dimensional torus.
And
if
who
for volume
was it?
preserving two-dimensional torus and still infinitely. And the strategies are the strategies that they are coming from the symplectic geometry, no? And it's difficult to see which are the dynamical interpretation of all those symplectic capacities that they introduce. On the other hand, there is another place where the connecting lemma or the closing lemma is known that this doesn't work. It's by the result of Michel Mann on Hamiltonian dynamics. So he produced this symplectic form. He produced a symplectic form and Hamiltonian respect to this symplectic form, such that all the energy levels are given by torides, and the dynamics on the torides are irrational rotation, and this is an open property. So this means that if you take a C-infinitive Hamiltonian perturbations, in all the energy levels are going to be toroidal, and it's not possible to close the trajectory. They are all C-infinitive conjugate to the initial one. So it's a very tricky construction because it's related how he defined the symplectic form. They have kind of irrational structure on the symplectic form. So it's another place where it wouldn't be possible to have a infinitely closing lemma in the Hamiltonian context.
Marie-Claude.
Yes, just I wanted to say that this kind of closing lemma is different from Charles closing lemma because in Charles closing lemma you approximate part of the orbit and invariant measure. And in Erie closing lemma you just create one orbit, but you cannot say that you, so for example, that the measure that are distributed along the periodic orbit are done in the set of the invariant measure or something like that. So you don't have the same application to ergodic theory. So it's weaker, I think.
Good point. I'm sorry, Enrique, who was the person who was giving the talk?
Hutchinson.
Hutchinson. Okay, not Hutchins.
Yeah, from Berkeley University. He's one of those guys in
Oh,
symplectic
Mike
geometry.
Hutchins? Michael Hutchins.
Yes.
Okay, not Hutchins.
Yeah, well, yeah, so it's Hucht. Uh-huh.
Yeah. Just
So those people are, it's very interesting what they do, and it is, but the math is not easy. It's pretty hard to show, but the results seem to be super interesting too.
Mm-hmm.
Yeah, no, it's amazing because also it's difficult to see. They produce some kind of symplectic capacity related to periodic trajectories, and they relate to some invariance of the dynamics. But it's difficult to understand what is the meaning, the dynamical meaning of those objects, the symplectic capacity, etc. So it's a challenge for us to try to give a dynamical interpretation of those objects.
All right. Is there anyone else who would like to?
So, Professor Wen, how do you say closing lemma in Chinese, and how do you write, and if it has some particular meaning?
We say in Chinese, we say 封闭引理. The meaning is just close. The lemma of closing.
The lemma closing. Can you write it for us?
Can you write here? I don't know how to write on the screen.
Is it 1B? 1B?
One what?
One?
No, sorry.
So, sorry, can you say it again, the name?
Oh, I mean, 封闭引理. 封闭 means closing. 引理 means lemma. In Chinese, we say 封闭引理.
Thank you.
You're welcome.
Thank you again for a lovely talk. Let's thank Lan Wen again. We have a 4-minute break until the next talk. The next lightning session. Okay, so everyone be on time. 4 minutes.
Since we are talking about closing lemma, I remember Charles telling me that, so you have the Arnaud closing lemma, right? You have an Arnaud and you can periodic points arrange. And he will tell us that you shouldn't call it closing lemma, you should call it closed lemma, because the periodic point is already there, so you're not closing anything.
There. That's good.
Pablo.
Yes.
Technical question. How do you raise your hand?
Right. So there is reactions.
Reactions.
Yes.
Okay.
Click
Reactions. Okay, got it. Thank you.
Right. Click raise hand.
Once I get to reactions, good.
I think we have to use, well, we might have to start using that just because.
Can I ask a question without raising a hand?
Who is that?
This is Andre.
Oh, Andre. Yes. Okay.
Hi, hi, Charles. Is this a cabin we went to once? Some 150 years ago?
Yes. Same cabin.
Okay.
You can see it's been improved a bit, a lot, in fact. But yeah, same cabin. Here, I'll turn the camera around. You can.
Wow.
I don't know.
Beautiful day too, right?
Beautiful.
Yeah. Anyway, it's good. Now I'm back.
I have a quick non-mathematical comment for Federico. It looks to me on the screen as though you've changed your name. Under your name is Sandra Lemma. There must be some meaning beyond that. I would like to know how to do that. There are statements I make that I don't want attributed to me, so.
My computer is not working good and I'm using my wife. Computer. It's easy.
Conan, would you like to put your slides up?
Oh yeah, sorry, I just went to the bathroom. So am I on the first? Am I the first guy to talk?
You are.
Oh, okay. Cool. I actually don't know the schedule, but cool. I'll try. Start share. Okay, one second. Yeah. Everyone can see this. Yeah, you can see this?
Yes.
Cool.
That's it. All right. Let me introduce Conan. So now we are going to start with the lightning session. The lightning sessions are going to be short talks, and typically they're going to be 5 minutes. So I'm going to our first speaker. It's a pleasure for me to introduce Conan Wu. She's going to tell us about the Bowen horseshoe problem, aka ergodicity of C1 and also diffuse. Thank you, Conan.
Yeah, hi. This is Conan, and I used to do math, and I don't do math anymore. So if I make any mistakes, I guess I have a license for that. So cool. And this is basically it's the ergodicity of the C1 and also of diffeomorphisms. As we all know, if it's C2 or C1 plus epsilon, and also then it has to be ergodic. But Charles keep referring to this problem as the Bowen horseshoe problem, so I decided to use that as well. Okay, so just a quick review. And also volume preserving plus C1 plus epsilon is ergodic. It's proven by Arnaud and found in every dynamical systems textbook. So basically the way to do it is do some kind of Fubini along the stable and unstable foliation. So you have a function that's you have ergodic, you have volume preserving diffeomorphism on a manifold. You take a characteristic function of a positive measure set, and you iterate it along the stable, and then so it's like it saturates the stable leaf, and then you use some technical stuff, i.e. Holder absolute continuity stuff. So C1 plus epsilon guarantees that this Fubini works, and then the function is constant almost anyway. So this is the classic, and as we all know here, Charles, I'm assuming a Charles-centered group, everyone knows C1 is. And so the natural question is whether this works in C1, right? And Bowen in the like in the 1960s, actually part of my screen is not. 1 second. So Bowen produced a horseshoe, i.e. using a homoclinic point on a torus, and then he was able to produce a C1 and also of diffuse that preserves a fat Cantor set. So you take a torus and you take a rapidly decreasing sequence of intervals, and you construct like a standard Cantor set cross Cantor sets, and that has positive measure. And then he was able to construct basically a cat map, but preserving a positive measure Cantor sets. To do this, basically, the map is actually a product map. So inside the outline I have here in blue, it's the map is actually a strictly just a product map, and it kind of sends this candle set in the blue to the same candle set in the red by stretching, on one direction and just wrap around the torus like a cat map. And so you would think like it's done, but the catch is that this map actually cannot be extended in a volume preserving fashion to the complement. And how you so this is actually a result I did in like undergrad. So if you have a fat candle set, then you have like the gap size eventually decreases really fast. I.e. it's old, so each gap is old of 1 divided by 2 to n times n squared. So if you will wind up with those squares that's in the complement of the candle set being much larger than the blue squares, which are the target of the map. Those, just remember this red volume minus the blue volume is about 1 over n to the third. Just carry that to the slide, to the next slide. And then what you do is you can use the isoparametric inequality because you have this the total side length of this red part of the intervals is about 1 over n to the squared. And then you apply F inverse, and then this square, as we know, will get mapped to this square, and then there will be extra volume that goes like outside of the gaps of the candle set. And then, so basically the volume of the enclosed by the blue, if the map is Lipschitz, then it has to be 1 divided by n to the fourth, and hence they cannot enclose volume of 1 over n cubed. So basically, so we prove that anything that's fat candle set cross fat candle set cannot be extended in C1. So what now? Basically, I think so. When I'm looking at this, like in the past couple of days, I think maybe in higher dimensions, because this current thing is very two-dimensional. You will definitely, when I draw some pictures on like even 3 or 4 dimensions, it seems like you will have a lot more space to play with. So I wonder if you can do like a Bowen cross Bowen cross Bowen in a T to the 2n, but it's like a very preliminary thought. And then another thing is like we can do maybe look at the necessary sufficient condition to volume preservingly extend a C1, i.e. Actually Bonatti, Crovisier, and Wilkinson did this for S1 to D. So if you have a C1 diffuse from S1 to S1, it always extends volume preservingly to a diffuse to D2 cross D2. So that I think that would be an interesting question to see like what kind of complex set does extend as a volume preserving. And that's it. Happy birthday, Charles, and thanks for being a great advisor, mentor, and friend.
All right. Thank you, Conan. Any questions or comments for Conan?
Your proof is very one-dimensional, right? Because you're using a product candle set. Is there any chance that a more complicated type of candle set?
Yeah, it was only for the product candle set. It's more it's the more complicated candle set is just like it's kind of hard to construct an I
mean, to get the action to work out.
That actually preserves the more complicated. Because it's an also it's kind of
So you think maybe in higher dimensions you could produce by the same method of volume preserving, I mean not by the same method, but by extension, a volume preserving non-Arnaud C1. And non-Arnaud, non-organic C1 Arnaud diffia.
Yeah, I was thinking that it looks like even if the thing is like even if I extend the thing that preserves the fat candle set, I still have to make sure it's an author, I guess. So I think there's enough space. It just there's some work to be done.
So maybe you could like make a foray back into mathematics and do that. What do you think? And then you could go back and do all your other stuff.
Yeah, if anyone has any ideas, mathematics is not my automatic state. I don't automatically start to think about it. But if someone has some ideas, shoot me an email, and I'll start to think about it.
All right. Thank you, Conan. Thank Conan again. Larry, are you around? I'm seeing you. Yes.
Yeah,
okay.
I'm here.
Hi.
Can I share my slides?
Yes, please. All right.
Hey, people see? Should I?
Yes, perfect. All right, let me introduce you then. Okay, now our next speaker is Professor Larry Guth from MIT, and he's going to tell us about the Kakeya conjecture in 5 minutes.
Thanks for having me. Around the time I met Charles when we were both at the University of Toronto, I became kind of bewitched by this conjecture, the Kakeya conjecture. So a line segment in every direction. And you could ask, what's the smallest area of a Kakeya set in the plane? First, you might think maybe it's the unit circle, so maybe the smallest area is pi. But actually, the smallest area is 0. Vesicovich made a construction in the 1920s. In any dimension, there's a Kakeya set with volume 0. If you want to understand, how big a Kakeya set could be, a follow-up question is, what can you say about the Hausdorff dimension of a Kakeya set? And in the 1950s, Davies proved that a Kakeya set in 2 dimensions has Hausdorff dimension 2, as big as possible. But in all the higher dimensions, we don't understand it all. So it's conjectured that a Kakeya set in Rn should have Hausdorff dimension n, even though it could have volume 0. And say in 3 dimensions, this is the best thing that we know. A 3-dimensional Kakeya set has Hausdorff dimension at least 2.50000001. So a big gap from 3. People got, I'm not sure whether Vesicovich was interested in this question. I'm not sure who first wrote down this question. But interest in the problem grew a lot in the 1990s. Work by Pfefferman, Bergan, and Wolf showed that this question is related to a bunch of other questions in analysis, in Fourier analysis, in PDE, and in number theory. So people got excited about it and tried quite hard to make progress on it. Okay, why is it hard? No one has found a counterexample to the Kakeya conjecture. But there are interesting configurations of lines that overlap a lot. If you have one line in every direction and if they were disjoint from each other, it would be obvious the Hausdorff dimension is at least n. So the enemy is that the lines overlap a lot. And there are interesting examples that we've found of lines that overlap a lot. And it's kind of hard to distinguish these interesting examples from an actual counterexample to the Kakeya conjecture. And here's one of them. Here's the most important one, the most important obstacle to the Kakeya conjecture. It's a set in C3, and it's the set that satisfies this equation. So it's almost like the unit sphere in C3, but there's one minus sign there. It's called a Hermitian variety, similar to something called the Heisenberg group. And it has lots and lots of complex lines in it. There's a 4-parameter family of complex lines in it, and through every point of this thing, there's a one real parameter family of complex lines through that point that are in H. So all these complex lines are overlapping with each other in a really interesting way. They don't all point in different directions, but On the other hand, they're not concentrated into any complex true plane. Okay, and part of the issue with the Cachet conjecture is to understand whether something like this could happen in R. That seems to be a hard problem. So H has it's a real hypersurface, has real dimension 5, which sort of corresponds to a complex dimension of 2.5. This number 2.5 is very important. So this like 2.5000001, that looks like a crazy number. But the point of it in our community is that it's a little bit bigger than 2.5. So this theorem by Katzyn's law says that there's no set that's really like this set over the real numbers as opposed to the complex numbers. So it manages to distinguish this Cachet imposter from a true Cachet set. But from a quantitative point of view, it's really poor. It's really hard to distinguish this kind of imposter from a true Cachet set in like a quantitatively robust way. And that is where the field is stuck today. Thank you for having me, and happy birthday, Charles. It's good to see you again.
Thank you, Larry. Any questions for Professor Guth?
Something like this. I mean, is it an algebraic question, or is there some way of constructing these crazy sets?
So the crazy sets all have this kind of algebraic feature. And so you might look for a counterexample, which is an algebraic set. And it's known, it's not trivial, but it's known now that there's no counterexample, which is exactly an algebraic set. And on the other hand, it's known that any counterexample has to be like kind of well approximated by algebraic sets at many scales and many locations. So the enemy is not exactly algebraic, but it has a lot of algebraic features. Maybe that's a clue, but I don't know how to come up with such a thing.
Are you looking for counterexamples, or do you believe the Cachet conjecture is true? Or both, I guess.
Yeah, I believe as a field that we've been a little remiss and that we should try harder. You know, after not proving the Cachet conjecture for 30 years, we should try harder to look for counterexamples. But I haven't really taken my own advice because I don't really know how to get started or what to do.
Any other questions or comments? All right, if not, let's thank Larry again. Thank you. Now, I think that this is Todd. Todd, are you there?
Yeah, I'm here.
All right. Larry, could you stop sharing your screen? Thank you. Perfect. Maybe, let me see how we time. Wait a minute and then we'll start.
Should I start?
Let me just give me a minute here. Right, let me introduce you. So no. Okay, so our next speaker is Professor Todd Fisher from Brigham Young University. He's going to tell us about the measures of maximal entropy for partially hyperbolic diffeomorphisms. Thank you, Todd.
All right, thank you. So I'm really grateful I can take, I guess, 5 minutes. First conference I went to as a PhD student was the Beyond Uniform Conference in Chicago in 2001. And as far as I remember, that was the 60th birthday for Charles. And so I thought I would talk about some work that is related to that. So that conference was eye-opening for me. I saw a lot of interesting problems and ideas. And one of the main things that I remember hearing a lot at the time was about stable ergodicity, which Andy spoke about just a few minutes ago. And the question there was specifically partially hyperbolic diffeomorphisms and volume preserving, and then the Lebesgue measure. Well, a few years later, I was at Maryland, and Jerome Bouzy was there for the year also. And he and I started looking at partially hyperbolic systems, but now in regards to other important measures. So specifically the measure of maximal entropy. And the question is, are there many questions about how much does the hyperbolic theory extend? So let me just say a few words about that. In the hyperbolic setting, let's say, for instance, the axiom A or an Osov, you always have a measure of maximal entropy. In axiom A case, there's only finitely many. They're supported on these transitive basic sets, and you can give a complete description of these ergodic measures of maximal entropy. So when we first started our research, we were talking about trying to extend some of these results to the partially hyperbolic setting, using kind of the maxim that a little hyperbolicity goes a long way. And our first results extended many of these, but more recently we've been seeing what the difference is between the two. So there's two different settings when you run into the partially hyperbolic case, which is in the center direction, what's its dimension? And so if it's one-dimensional, or if the center at least splits into one-dimensional subbundles, there's always a measure of maximal entropy because it's entropy expansive. And then if you have compact center leaves, at least for a large class of them, there's at most finitely many ergodic measures of maximal entropy, and there's a way to classify these and describe them. And on the other hand, for certain transitive partially hyperbolic diffeos near the time t map of an Osov flow, you actually can get typically two ergodic measures of maximal entropy. So you can't just decompose into kind of your transitive components. There's something more about what is the support and how can you distinguish these. So one question I have is, in the case of a one-dimensional center, or at least splits into these one-dimensional subbundles, are there always a finite number of these ergodic MMEs? How can you distinguish them? And more specifically, when is there a unique one? When it's unique, there tends to be very special properties that have arisen in these situations. And when can you classify that? And what can you say about the support of these measures? I've been watching the time, but I hope I'm doing okay. Now, what about with higher dimensional center? So when you have a higher dimensional center, things get much more difficult in this setting. So in a work with Jerome and Sylvain and myself in 2018, we showed that if you have a volume preserving diffeos that are generically C1 on closed manifolds and no hyperbolicity, so no dominated splitting or partial hyperbolicity at all, then there's no measure of maximal entropy. So the question is, which one wins, the hyperbolic direction or the center direction with these higher dimensional centers? So for an example, if you take an Anosov, cross one of these examples, you get a partially hyperbolic with a higher dimensional center that does not have a measure of maximal entropy. So can you say something about this? Is there an open and dense set then that would have to have a measure of maximal entropy, finitely many? How can you classify these in the higher dimensional setting? So those are my two questions. First of all, for one-dimensional subbundles, and then higher dimensional. It's going to be very different techniques and problems in general. And I think that's about my 5 minutes, so thank you.
Thank you, Todd. Any questions or comments for Todd? I have one small comment then. I think that the first who brought the existence of measures of maximal entropy for the and also for the partial hyperbolic case is It's a work of Laysan Young and Newhouse. It's from the 70s, almost.
Yeah,
before the
yeah.
70s.
Mm-hmm. Yep. Yeah, they did. Yeah.
There is that. I think that well appears using the entropy expansiveness.
Yep.
Right. Let's thank Todd again. Thank you, Todd. Katie, are you around?
Yep.
Ah,
Shall I share
perfect.
the screen?
Yes, please.
Great.
Okay, so let me then introduce you and we'll start. Our next speaker is Professor Kathryn Mann from Cornell University, and she's going to tell us how many Arnaud flows can you put on a closed hyperbolic dimension.
Thank you. Thanks. It's a pleasure and a delight to be here among such an all-star lineup of speakers. I like the type of questions that probe the interplay or the relationship between the topology or geometry of a space, the algebraic structure of a group, and the possible dynamics of actions of that group on this space. So here's one that I can explain in 5 minutes. In this case, our group is R, so we have a flow. And our question is, how many Anosov, that's dynamics, right, flows, can you put on a closed hyperbolic three-manifold? Okay. So for context, here's a version of this question that is famous, that many of you here know better than I do, for sure. Smale asked in this 1967 survey paper, which compact manifolds emit Anosov diffeomorphisms? And conjecture, now with lots of evidence towards it, is that the manifold should be locally modeled on some nilpotent Lie group. And the types of Anosov diffeos you see are automorphisms, right? So as well as answering this question, we have a classification almost theorem conjecture. The flows version of this, though, is already much harder, even in the smallest dimension where it makes sense to ask for three manifolds. So here's the question: which compact three manifolds emit Anosov flows, and can we classify them? Now, when I say classify here, I'm not being a dynamicist; I'm being a topologist. All right. So Anosov flows to a topologist. I can't see regularity. I can't see the passage of time. What I can see, though, is two transverse foliations as well as one-dimensional foliation by orbits. So when I want to classify, I'm classifying up to orbit equivalence, where two flows are equivalent or the same if there is a self-homeomorphism of your manifold taking the orbits of one to the orbits of the other. Okay. So that's the topologist version of classifying flows. And in the three-manifold setting, this is not just restricting my question to a case where it's easy to solve. It's a case where it has a lot of relationship with geometric topology. So three manifolds, crash course, right? What's the structure theory? You can decompose a three manifold along spheres into its prime summands or irreducible summands. And then each one of these irreducible parts, you can further decompose along tori into geometric pieces. There's my cartoon. I have a hyperbolic piece, a Euclidean piece, etc. There are some long-known topological constraints on admitting an Anosov flow. So your manifold, following from combined work of a few people, must be irreducible, and so no sphere decomposition. And the fundamental group must have exponential growth. That's Margulis for three manifolds. And that rules out some geometric structures. We also know that if you have a non-trivial torus decomposition, there's lots of ingredients that build examples of Anosov flows on such manifolds. But for these geometric pieces, sometimes geometry is enough to buy you rigidity. So if you have a ciphered fibered piece, then you look like the cup on a surface. Right? If you have a solvable, if you're one of these sort of solved manifold geometries, then your flow is the suspension of an Anosov diffeomorphism on the torus. And in particular, on a fixed manifold with this structure, there can only be two Anosov flows at most up to orbit equivalence. But for hyperbolic, the most interesting geometry, at least according to me, well, it's the Wild West. All right. So here's a question from Kirby's problems list from the 70s attributed to Christie. Can a hyperbolic free manifold admit arbitrarily many Anosov flows? And Jonathan Bowden and I answered this like last year. You give me a number, 25,000, I will build you a designer hyperbolic free manifold that admits at least 25,000 distinct Anosov flows. The proof of this is just a smorgasbord of techniques from geometric topology and sort of standard constructions using everything from Dane surgery to Mossbat rigidity. But we still don't know if you could put infinitely many Anosov flows on a single hyperbolic manifold. All right, ours get more complicated as you ask for more. And the classification problem in general is just way open. So my last picture here, as we're ending, is a kind of hint of why I like this classification problem also. How should I start thinking about this? Well, we like to think about the orbit space of a flow, collapse every flow line to a point. Locally, this isn't very interesting, but if you lift your whole picture to the universal cover and look at the orbit space there, you produce a different kind of a group action on a space with fascinating dynamics. The action of the fundamental group by deck transformations extends to an action at a compactification of this of some circle at infinity that sort of sees the structure of these transverse foliations. And so this brings me back to a long time favorite question, which is understanding groups acting on the circle. But that's, I guess, another question for another day. Thank you very much. Happy birthday.
Thank you, Katie. Any questions? Conan?
Conan, yeah.
Yeah, are you talking about compact hyperbolic manifolds? Because why can't you have a one parameter family of Anosov flows if it has like, you know?
Oh, I want, yeah, compact. That's a necessary restriction, not to make any example. Yep.
Any other questions?
Why can't you look at the action? I mean, not why can't you, but if you look at the action on the boundary at infinity, the thing you like, is there any hope of classifying these kinds of hyperbolic actions? You know, like on the number of attractors you get or some craziness? Have you got it?
Yeah, you want like a convergence group theorem or something that says like everything that has this kind of dynamics comes from one of these examples. Yeah, I don't know. I'd love that too. I don't know.
But you don't have it.
We have some framing of it like an Anosov like action on a bifoliated plane. There should be a nicer version of this, but I don't know. Mm-hmm. I should say this picture, you know, sort of is inspired by work of Barbeau and Fenley, and is stuff I'm thinking about now with Thomas Barthelme and Stephen Frankel.
Any other questions?
Just a comment that I think it's fascinating how there's been such a revival in interest in understanding, classifying, and Anosov flows in dimension 3. And I think part of it probably came from trying to understand partially hyperbolic diffeomorphisms in dimension 3. Anyway, it's great. Cool.
I have a question for you, Katie. It's very ignorant, but okay. So suppose that you have a manifold, a free manifold that supports a non-transitive Anosov flow. Does it support a transitive Anosov flow?
Ooh. I don't know the answer to that question. But I also haven't thought about it, so there might be an easy answer that's like, oh yeah, here's your counterexample. But let me think about that. If I figure it out in the next, hour, I'll let you know.
Great. Thank you. All right, let's thank Katie again.
Thank you.
last speaker for the lightning session before the break. It's gonna be okay. So Martin already shared his screen. Right. Let me give 1 minute, and then I'm not seeing you. Where are you, Martin?
Okay. Are you not seeing me?
Now I see.
Okay, I have to say something for it to make me smile.
Great.
Great.
All right. Let me then introduce you. Okay. So the last speaker for this lightning session is going to be Professor Martin Wattenberg from. I'm sorry, I'm mispronouncing your name, but okay. He's from Harvard University, and he's going to tell us from dynamics to visualization and back again.
Great, thank you. So first of all, I just have to say it's fantastic to see you again, Charles, to see old friends from Berkeley who I haven't seen in a long time, and also looking around, basically everyone who wrote the papers and textbooks that I was studying for my quals. So this is fantastic. I'm a little bit of an outlier here, and so this is more of a palate cleanser than heavy math, what you're going to see. And I want to describe a little bit about sort of my zigzag career path that, after graduating from Berkeley, I became a journalist somewhat randomly because I was fascinated by the web, got interested in data visualization, ended up at IBM, sort of turned into a computer scientist almost by mistake, and spent a long time at Google, got interested in machine learning, and today I'm a professor at Harvard in the computer science department and in the business school. So the theme of this whole weird zigzag career, which I have to say is sort of like a homoclinic orbit with respect to academia with all the attendant chaos that implies. The theme of the career, I would say, is turning numbers into pictures. And in retrospect, this should have been obvious because thinking back on all the meetings I had with Charles, I think I drew maybe like 3 or 4 equations the entire time. Almost everything was figures. So the things that I've been doing since then have looked like translating music into pictures, baby names, seasons, the stock market, and so forth. So what I thought I would talk about today is something that's a little bit more dynamics related. And this is a project that began as an art project, but then had some interesting applications in other places. And it came from sort of a place of being interested in what does the wind look like? And it's with my longtime collaborator, Fernando Villegas. So this is actually an old problem to try to figure out what the wind looks like. What you see here is an image from Edmund Halley of Halley's Comet from the 1600s. It's actually not a bad drawing, although very oversimplified. And you can ask, what does the wind look like in detail? So here's where I'm going to just switch to a visualization. I'm going to tell you what we did, though. We thought about, okay, what is air? It's a bunch of particles. We're going to set a bunch of particles moving and show their trails over the United States. And we got some nice, let's see, all right, let us, some data. So what you are seeing today is relatively up-to-date data of the wind over the United States. I don't know how well the animation is going to come out over Zoom, but you have to picture this at least looking like a smooth flow, even if it looks like just a C0 flow to you. And I can zoom in. I can sort of see today there's a lot of interesting stuff happening in the Midwest. I know some of you are in the Bay Area, so let's zoom in there. This is actually sort of a, I don't know, dull day. I think it looks like very little wind. So I'm going to unzoom. But this gives you a sense of the complexity of the wind over the US right now. It is very different from that Edmund Halley view of, it's smooth, basically it's all the same all over. This is where I think there's interesting questions come up of the interplay between the math of the dynamics and the visualization. So here's an old image of a hurricane. This is Hurricane Isaac. And one thing that's, it's a very dramatic image, I think, because you can see sort of the eye of the hurricane as a landfall in Louisiana. But one thing that's a little bit weird is that eye looks very large. It looks like it's, all of Louisiana. But if I zoom in, you can see actually the eye is much smaller. And in fact, as I zoom in, that little empty area is getting smaller and smaller relative to the map. And so what this tells us is that there's something about the way that I've been choosing the dots to put in and to let flow in this map that is not quite on target, that it would be much smarter to take some of these little dots moving around in these other areas where we have plenty of detail and to add them back in this hurricane area. What is the best algorithm to do that? How should you choose the dots to make it clear? I don't know, but it's an interesting math question. I will put it out there for discussion. Let me show something else. Let me bring up another interesting past today. This is sort of a random day in March in the past. I find this a very beautiful image to look at. It's very soothing if you look at all the ridges and the lines. One thing that's a little bit weird is these very dramatic sort of white ridges. I don't know that they have a lot of physical meaning. In a sense, they're a little bit of an artifact from the fact that I'm letting some particles sort of get drawn into these attracting areas, kind of some sort of attracting basin. You can sort of think about this as maybe I don't know, integrating a bunch of measures or kind of getting close to an invariant measure, but it hasn't converged yet. It's at the same time, even though it's a little bit deceptive, like that air isn't really more dense, it also makes it very beautiful. And so this is another example of the kind of problem you see in visualization of trying to tune the math to be both correct on the one hand, but also show things that are going to appeal to people on the other hand. Okay, with that, I'm going to go back to presentation and talk a little bit about what you can learn from this flow. There's a third thing that's interesting, which is that this began as an art project, but it turned out at the time it was basically the only detailed real-time wind map available for the US. And so I and my collaborator got these messages that were a little bit frightening. So it was all about people using it for real things that made a difference. Sometimes it was like bird migration. Sometimes it was farmers. There were pilots, which deeply freaked us out because this is surface wind, not above. And in fact, we ended up having to put sort of a big warning on the map saying, please do not use our art project to fly a plane or sail a boat or fight wildfires, because these were all things people were doing. And I think that speaks to both the universality of math and a little bit of the perhaps undue power of visualization, which is something we should all think about. This also ended up influencing a lot of things. So this type of visualization was taken by a lot of TV stations. There's also a fantastic globe version that came out by a guy named Cameron Beccario. And if you look at for wind map globe on Google, you'll see one that goes much farther than the one that we made. And if nothing else, it's a beautiful illustration of the Hairy Ball theorem. So this ended up in the Museum of Modern Art. Had surprising reach in the end. And I think it just shows the appeal of flows, even sort of simple 2D flows that are smooth and just on a disk, essentially. So with that, I'd just like to say thank you once again to Charles. You were an amazing advisor for what was probably a somewhat peculiar student, but you were very supportive and kind and helpful, and happy birthday.
Thank you, Martin. Great. Any questions?
Can't you teach us in class at Harvard?
I'm going to start teaching in the spring. I'm teaching this funny arrangement where I'm teaching one semester in the business school and one semester in computer science. And in the spring, I'll probably teach a course. It's a little bit to be determined, but probably on communicating around data. And then I'm hoping to teach a course in software art next fall. This particular semester, I'm not teaching.
Awesome.
I have a question for you about the data. So what is actually measured? Just the wind speed at all of these places, and they produce a table?
Yeah, okay. So it's an interesting question. So the actual data you're seeing is a little bit weird because what it is, it's the only way to get something that's relatively close to real time is to take this 3-hour projection that the government does, and they sort of give you a big table of a bunch of numbers that are sort of essentially latitude, longitude, and then you get sort of a north, south, and east, west component. to the wind. And then there's a whole bunch of data processing, because it's in a truly horrific format in many ways, to get it into a version that is suitable for the web.
Thank you.
One of the topics that has attracted quite a bit of attention in applied circles the last few years are finite time Lyapunov exponents. Ooh. I don't know whether that's a term that you've encountered, but basically trying to compute the stretching and contraction in different directions. And I'm wondering whether you can take the processing that you've done of the data and produce statistics of that sort.
Yeah, I mean, it's interesting. It sounds like you're essentially sort of explaining the type of, if you look at what's dense and what's not, that's closely related to that question that I brought up. Presumably, yes. Like, this is not doing any fancy, math or computation. It's really a very, very simple simulation. But I bet so, yes. And I bet you could find ways to visualize that are really nice. There's interesting sort of 2D tensor visualizations that I could see being directly relevant. I'd be happy to talk more about that too, if there's interested in finding new projects now that I'm in academia.
Sheldon has his hand raised also.
Oh, yes. Sheldon? No.
It's left over from before. I'm sorry.
Okay. Well, then let's thank Martin again. And now we'll have a break. We'll have a virtual coffee, depending on your time zone, I don't know, dinner, lunch or something. We'll come back in, so now what is it? It's 8:45? 55, I think. So we'll come back at 9:45.
Ending. How long are we going to?
Of Marie-Claude's talk?
No, the whole conference.
It's going to end at noon California time.
Oh, okay.
Yeah. So, so Marie-Claude, do you want to bring up your slides?
Noon in California?
Yeah.
What time is it now in California? 10?
2 hours before that.
Uh-huh.
10 a.m.
I see. Right. Okay, you're right.
We were supposed to start 5 minutes ago, so.
Yeah, it's 10 minutes of 10 or so.
Okay, so we were supposed to, it's a little, okay. So I will introduce, so Marie-Claude Arnaud, who's, oh my gosh, now she's in Paris and I've forgotten her affiliation.
I'm in the University of Paris. That's the true name.
The University of Paris.
Yes, very simple.
And I remember having a conversation started by one of my graduate students about submanifolds of partially hyperbolic systems, normally hyperbolic submanifolds, and what kind of dynamics they could support. And so I asked Charles, and then Charles was like, I don't know. And then we asked Marie-Claude, and then we got a really good answer. And so this seems even kind of related. So anyway, welcome, Marie-Claude, and you have we'll give you the extra time. So thank you.
Thank you for the invitation, and I'm very happy to be there.
Recording in progress.
Well, I learned about Charles' work on closing lemma when Michel Herman asked me to explain the major proof of this lemma. And I think I spent at least 10 years on these topics, and even the extension of Hayashi on connecting lemma, and it was really great work. Now I changed a little, and today I will speak of objects that have no periodic point, so no closed orbit, but I hope it will be okay. And so today I will speak of twist map. And just before explaining some result and question about twist map, let me just introduce some vocabulary. So A is an unbounded annulus or cylinder, and well, some results are on the bounded annulus, in fact, but it's simpler to explain what is a twist map on the unbounded annulus. So, and for me, a curve is always a loop, so a topological embedding on the circle in the annulus. And a C0 graph is the graph of a continuous map, and a Kn curve for some dynamics is a smooth graph on which the dynamic is smoothly conjugate to a Diophantine rotation. So that was in all the talk. And so we study symplectic twist map because they are useful for a lot of problems. And for example, let me recall that Birkhoff billiards is modeled by a twist map, and the theta.
I'm sorry, let me
yes.
interrupt for 1 second. Can everyone who has your, mute your speakers, please, because there's background noise. Mo, can you mute your speaker?
There's no noise coming from here.
Well, okay, but okay, the noise is over, so fine. Sorry, please continue. I'm sorry.
Okay, and so Birkhoff billiard is modeled by a twist map on a bounded annulus, and the theta coordinate is just the coordinate along the boundary of the billiard. So, and the r coordinate is the sinus of the reflection angle. And also a symplectic twist map close to some general elliptic fixed point can be modeled by a twist map defined not exactly on a bounded annulus, but it's a twist map by symplectic angular coordinates that are not exactly the usual coordinates, polar coordinates, excuse me. So let me recall the definition of a twist map. So a twist map is a diffeomorphism of the annulus that is homotopic to the identity, so it preserves the ends and also the orientation. Because it's symplectic, it preserves the area, and it twists, F twists vertical to the right. And this means that if you take any vertical line, so you take the image of the vertical and you project on the first coordinates, then you obtain an increasing diffeomorphism. Of course, you can define also a twist map to the left, but I choose the twist map to the right. And there is a picture for twist map on the bounded annulus. And I will denote by TR the set of, so I didn't define exact symplectic twist map, but the set of symplectic twist map endowed with CR Whitney topology, and R is between 1 and infinity. Okay, and there are some well-known examples. So the first one is very simple. It's the case of completely integrable twist maps. So theta is mapped on theta plus T of R, where T is a C1 increasing diffeomorphism of R, and R is preserved. And so you have an invariant foliation that is smooth, and the dynamics on each circle of the foliation is just a rotation, and the angle of the rotation increases when you go up. And there is another family that is more complicated. That is a standard family that depends on one parameter, lambda, that is a real parameter. And here you have the formula, and you can observe that when lambda is 0, you have a completely integrable twist map. But So when lambda is small, you perturb a completely integrable twist map, and in this case, because of KM theorems, you have invariant KM curves. But you can prove that when lambda is large enough, you have no invariant curve. So here is for small lambda, and then lambda increase, and at some point, you have no invariant curve. And I will be interested in the invariant curves, and I will be interested in the question of their regularity. And if I have time, I will explain the link of this question with integrability questions. Okay. So there is some easy construction. If you have a CK graph, then you can build a twist map that is CK, such that the graph is invariant by the twist map. What you do is, so you have your CK graph, you take the diffeomorphism that put your CK graph onto the zero section, that is a vertical translation in the fiber. And because it preserves each vertical line, then when you conjugate a twist map by such a map, it's a twist map. Only this symplectic twist map that is integrable, and it preserves the zero section, and you conjugate, and the conjugate twist map so leaves the curve C invariant. And I will be interested in the converse. So imagine I have a CK dynamics and I have an invariant curve. Can I say that the curve is as regular as the dynamics is, or a little less, but differentiable? And there exist some regularity results. So the whole result of Birkhoff. So Birkhoff proves that if you have an invariant curve by a symplectic twist map that is non-homotopic to a point, then this is a graph. This is a C0 graph. And after that, he proves that this C0 graph is in fact Lipschitz, and even that the Lipschitz constant of the graph is locally bounded from above, locally, so in the set of invariant graphs. And so locally, these graphs are uniformly Lipschitz. And so their set is closed if you put of them, for example, the Hausdorff topology, or if you put on the set of maps with this graph, the maps with graph are invariant, the topology, the uniform topology on the set of maps. Okay, so there are Lipschitz, but there are examples where they are not differentiable. We know that a Lipschitz map is almost everywhere differentiable, but if you look at the case of the pendulum, that is a very simple Hamiltonian system, and you take the flow for small time, this is a twist map. And there are a lot, of course, of invariant curves. Some of them are smooth, c'est infinite, but the separatrix of the hyperbolic fixed point, they are not smooth, the separatrices, because you have an angle at the hyperbolic fixed point. So there are examples where the invariant curve is not very smooth, even if the dynamics is smooth. Okay, but there is a fixed point of this invariant curve. And as we will see, having an invariant curve that contains a periodic point is not a typical property for symplectic twist map. And more precisely, there is a G delta subset of the set of twist map for any topology between 1 and infinity, such that a twist map in this set has no C0 graph that contains a periodic point. And the method to prove that is to make the periodic point generic in the following sense. So you will add that the eigenvalue of all the elliptic periodic points are non-resonant. And if this is the case, because the invariant curves, the invariant graphs are Lipschitz, you can prove that an invariant graph cannot have an elliptic, such an elliptic periodic point. And once you know that the invariant curve, if they contain a periodic point, it has to be hyperbolic, you just use the fact that generically the stable and unstable manifold of periodic points meets transversally. And so there is no curve, regular curve joining the two periodic points. Okay. So the example I gave just before, this is not for typical twist maps. Okay. There was another situation that was studied by Michel Mann. Not this one, excuse me. Okay, no, it's, excuse me, it was the slide at top. Okay, and another remark is that, on the contrary, there are curves that remain after perturbation. There are open set of invariant curve and smooth invariant curves. So open set of dynamics that have smooth invariant curve. So this is when you can apply KM theorem. So if you have a smooth twist map with a KM curve, then you know that every twist map that is close enough to this twist map has also a KM curve. Okay. So now, instead of looking at typical dynamics, I look for some curves at their typical property, and this was what Michel Mann studied. So Michel worked a lot of KM theory, and he was interested in the set of smooth twist map that has at least one KM curve, one invariant KM curve. Curve. In fact, you have a lot of other KM curves that accumulate this one. And you can look at the closure of the set of the KM curves. That is larger than the set of KM curve. And it proved many interesting properties. For example, one striking property is that the rotation number of a typical curve is not Diophantine, Cuville. But what is interesting for me is that, for us, is that it proves that in this set, the typical property of the curve is that such a curve is C1. So it seems that often the invariant curve are C1. And I have also a result. I prove that if you can say a little about the dynamics, but it's strong in fact, if you have an invariant curve that is a C0 graph, on which the restricted dynamics is Lipschitz conjugate to a rotation, then the curve is C1, and the conjugacy is C1. And so now, of course, you ask the question, is it possible to have bad regularity for an invariant curve that has no periodic point? that is invariant by a symplectic twist map that is smooth enough. And when you ask this, maybe you want a method to build counterexample. And there was, so Michel Herman introduced such a method in his Asterix volume. So this is the following method. So you consider the generalized standard map. So instead of putting lambda sinus, I put phi. Phi is some function. And if you look at some invariant graph, so the graph of a continuous function psi by this dynamics, so what you observe is that the projected dynamics is just theta gives theta plus psi of theta. So this has to be an orientation preserving homeomorphism of the circle that I denote by G. And moreover, if you write the functional equation that tell you that you have an invariant graph, you arrive to this nice equation, functional inequality. And so the idea to build example where you have a regular dynamics and a non-curve is to say, okay, I want to take a phi and phi is the invariant curve. I will take some invariant curve that is not regular, psi. So I will define G. G is identity plus psi. And I will try to build G in such a way that the irregularity of G and G minus 1 will cancel. And I will obtain something that is more regular. And so phi that defines the dynamics will be more regular than the invariant curve. So that is what the question in this class of twist map is it possible to find a non-C1 orientation preserving homeomorphism G of T such that G tilde plus G tilde minus 1 is non-regular, is regular, excuse me. And a lot of people use Herman's idea. So firstly, Herman built a C2 twist map that have a non-C2 invariant graph with an irrational rotation number. And it's non-C2 because the dynamics, the restricted dynamic is dangerous. And so it cannot be C2 because of the dangerous example. So I built some similar example where the curve is not differentiable and the twist is C2. But the dynamic is dangerous, and so now the new question was, is it possible to obtain a non-differentiable invariant curve on which the dynamic is minimal? So C0 conjugate to an irrational rotation. And using the same method, the same class of example with so the generalized standard map, Avila and Fayad built a C1 twist map that has a non-differential invariant graph on which the dynamics is conjugate to an irrational rotation, C0 conjugate. But their method works only in C1 topology. And so my question and my problem is it possible to find a smooth twist map? A smooth twist map that carry an example similar or similar to the one of Herman also because it's unknown. So that carry that has a non-smooth, non-C1 invariant curve in which the dynamics is maybe minimal or even dangerous. And this is completely open. If it's possible or not. or if we have to look for an example in a higher family, I don't know. And there is a related question of Mather. And the question of Mather was about the integrable twist map. So it's not the definition I gave of completely integrable twist map, but so you assume that you have a twist map and that the whole annulus is foliated by invariant C0 graph. For example, you can assume that the twist map is smooth, but and the question is the foliation at least C1, or is it does there exist some example where the foliation is just continuous? And what is interesting is that if you can prove that the foliation in C1, you can say that the dynamics on the invariant curve is really conjugate to a rotation. And we don't know, for example, if for such a C0 integrable twist map, if there could be Dangerois dynamics on the invariant curves. It's an open question. Okay, and in fact, I have finished and I have just a picture for Charles closing my lecture. Thank you.
Thank you.
May I ask a question?
Of course.
So, one situation which has been always interesting to me is what is called the last invariant circle. So in case of standard math, this is a case studied by McKay for the standard rotation number. And so there's a parameter value for which there is a last invariant circle. And so the question is, do we know anything about the regularity of that thing? For example, is it C1? Is it Dangerois? Not Dangerois? I'm sure trying to understand what we might possibly know about that thing.
What we know is that it's not Km because it will remain. You ask the last in the set. You fix the rotation number and you.
Yes, right. But let's say golden mean. That's the one. And so at some point, at some point, there is a parameter for which it's there, and then if you increase it, it's no longer there. So this thing is not in the open. This is in the boundary of this sort of Hermann kind of like examples. But I don't know if one can say anything about whether this is a Dangerois, non-Dangerois, how regular this thing is, and so McKay had a big thesis about this, but I'm not sure if there have been any results on that afterwards.
No, I don't know the answer, of course, and I heard about result proving that it's not C2, but I never found this result, and no, I have no idea. It's yes, a recurrent question, yes, an interesting question, but no idea how to prove this.
All right. And in Mather's question, you said the foliation is not C1, so you would allow for even an example where the leaves were C infinity but did not vary in a C1 way. Like that's open as well. Or could that not happen?
Well, so your question is if we know something on only the leaves? That's.
Well, just the question was, does there exist an integrable smooth twist map whose invariant foliation is not C1?
Yes.
And I was wondering, are you talking about the smoothness of the curves in the foliation?
No, in fact,
talking about how they fit together transversely.
Yes. Yes, so, because if it doesn't say that the dynamics is rotation if you don't control the transversal. Yes. But Lipschitz is enough, in fact.
Yes, okay. Thank you so much. Let's thank Marie-Claude again, and let's not take a break. and just have Sylvain start in a minute. Okay. So thank you again.
Thank you, thank you. I was very happy to speak at this for Pugh, for Charles' birthday. Bye.
So yeah, if you can stop sharing. Okay. Sylvain, can you share? And Pablo, did you want to introduce this talk?
I can do it. All right. So our next speaker is Professor Sylvain Crovisier from CNRS, from Orsay. He's going to tell us about the periodic set of diffeomorphism. Thank you, Sylvain.
Thank you. Hello. Good morning, Charles. So it's emotional for me to celebrate you today, since your work has been so decisive for mine. I have to say that I have been, I felt very honored 12 years ago when you accepted to participate to the committee of my habilitation defense. And always I have been fascinated by your closing lemma. It took me time to digest it. So I learned it first from Marie-Claude's book some time ago. And so today the rule was to talk about open problems, questions. So it was difficult for me not to talk about periodic orbits. So I would like first to remind that some time ago in 1975 or just before maybe, you proposed yourself, or you collected yourself with Jaco a list of problems in dynamics that have been very inspiring, and now it's very interesting to see the way, the progresses that have been done in dynamics. So to start the discussion, I will come to these problems, to two of these problems. So one is in fact the one you worked on. It's also about the closing problems, or the density problem, density of periodic points in the set of, in the non-ordering set or in the recurrent set. So does this occur generically in a CR topology? And so you show that it is a case when you consider the C1 topology, and your work was very important to start what we could call the C1 generic theory that has been developed then over the years. But what happens in higher topology? So, well, it has been mentioned by others, but I put a list of some results that have been obtained a bit before, but then for some, but for many afters, in different settings. And so I don't list all of them, but so I have two remarks. One is that, in fact, for most of them, what is behind is either you have some hyperbolicity, so it's very clear for the Anosov closing lemma, or you have one-dimensional structure behind. So, for instance, you have the result on interval maps by Lai Sang-Yong. It could be mixed if you consider the partially hyperbolic systems with one-dimensional center. And for some of them, there is no, it's not necessary to perturb. The periodic points are, I think you call that, in this case, you say that there is an already closed lemma, yeah, right? But there is, in general, a huge difference between these results and you. So first, because you have more structure in general for this result, but also because, as Marie-Claude mentioned, they are less precise. They give the fact that periodic points are dense in some recurrent sets, but they do not give any information on the support of this periodic orbit, whereas in your proof, you built your periodic point from the orbit that already exists. So you have a second problem in your list, which is related to that. So when you have a recurrent point, not only you want to build a periodic point through that point, but you would like that the new orbit, the new periodic orbit, shadows part of the initial one. And so this is possible by the technology you introduced, and that has been improved later, in particular by, for instance, Hayashi, his connecting lemma. And so I mentioned some results that have been proved in this direction, and that gives some information on the support of the periodic orbit that you can create. And this has been very important for the developments of the C1 dynamics. So not only it's good to have periodic points, but you need some information about these periodic points, and you want to see how they are linked together. Okay. So I would like to emphasize the difference. I will present one of the connecting lemma, a closing lemma, one case beyond the C1 topology. So this is a result I have proved recently, some years ago, with Enrique Pujals, which applies to surface dynamics, which is enough dissipative, and which in particular applies to any Henon map whose Jacobian, whose determinant, so is less than 1/4. Okay. So the conclusion is that for any such map, you don't need to perturb, and the support of any invariant probability is contained in the closure of the periodic points. It's inspired by the result I mentioned by Lai Sang-Yong on the interval. So she proved a similar result with a weaker assumption on the recurrence. She only assumed that she only assumed that the point is recurrent to show that it is approximated by periodic orbits. So how to do? There is a key property for these Henon maps. I won't explain why. So, well, you first can reduce to a region, and then inside any point which is typical for an invariant probability. So since you're dissipative, it has a stable manifold, a curve, and this curve escape from the disk has to go up to cross the boundary of the disk, and so it separates the disk into parts. And so the goal is to approximate this point by a periodic point. So you iterate the point, and by recurrence, it will come close to itself at some time n. And when it's close, let's call G the new map, the iterates which bring X close to itself. Okay, so this split the disk into 3 regions, and the goal is to build a periodic point in this intermediate strip. And since you have a contraction, if you do so, in fact, the periodic point will be close to X and G of X. Also. Not only you not only localize horizontally, but also vertically. So you work with G, this iterate of F. So you know that X is mapped to, on one side of the strip is mapped to the other side by G, but you continue to iterate. So maybe during the first iterate, it goes to the right, so to this half disk that I call D+. But by recurrence, after some time, it has to go to the left. So you take K, the first iterate, such that at time K plus 1, the point goes back, exits D+. Okay. And so now you have your disk is mapped into itself, and you introduce a retraction which collapses the disk to the strip R. And just by Brouwer fixed point theorem, you have a fixed point by this, the composition of GK with this retraction. You have a fixed point in the image, so in the strip. But it's a fixed point in principle not for GK, but for H composed with GK. But now you remark that the fixed point cannot occur on the boundary of the strip because the boundary containing X is mapped to the right, and the boundary containing J of X is mapped to the left by JK. So in fact, this fixed point has not been touched by the retraction, and so should be a fixed point for GK, and so a periodic point for F. So very well, we have found a periodic point. We don't need to perturb. But you see here that we have no information about this orbit. We don't know how it travels in between. Okay, so it was an illustration of this kind of closing lemma that exists for our already closed lemma. Okay, so what I would like to say now is that, okay, very well, we have periodic points in a good case, but it's not, want is to explain how they are together, how they are organized, so that together they can give some structure and explain the dynamics. So for that, let me introduce some relationships between the different periodic orbits. So the periodic orbits are O or O prime here, and I assume they are hyperbolic. And so you can introduce what's called Smale's preorder if you have heteroclinic orbits between one periodic orbit to the other one. So the unstable manifold of the first intersects, let's assume transversally, the stable manifold of the second one. And if you can also go back from O prime to O, you have the other relation, then you say that these two periodic orbits are homoclinically related, and this defines an equivalence relation between periodic orbit and the equivalence classes. When you take the union and the closure, define the what we call the homoclinic class, which are very good, very nice set of the dynamics because they are transitive and fit by periodic points, and you can play with the periodic orbit, the homoclinic orbit, and get some information. So here, for instance, an example on surface where the dynamics is decomposed, you have a source, a sink, and one homoclinic class, non-trivial. Okay. From Newhouse example, Newhouse construction, one notices that there may exist infinitely many disjoint homoclinic classes, so the picture may be quite complicated. So the question now would be how these different homoclinic classes are organized together. If there are infinitely many ones, how do they accumulate? Huh? Okay, so this is the question I would like to discuss today. From this viewpoint, so I want to introduce strengths for a periodic orbit. So I assume the periodic point to be hyperbolic, and I want to measure the hyperbolicity. So periodic orbit has Lyapunov exponents, which are related to the eigenvalues of the tangent map at the period, and so the periodic orbit is hyperbolic if the Lyapunov exponents do not vanish, and you measure the hyperbolicity by taking the minimum of the moduli of the Lyapunov exponents. And so my question is the following: consider any sequence of periodic orbits, then you may expect the following dichotomy. So either among this sequence, you may find two of them that are homoclinically related. If they are all independent, then you should observe some degeneracy. So the hyperbolicity should go to 0. Okay. So why do we expect that? That's because hyperbolic periodic orbit have stable and unstable manifolds, and you may expect that the hyperbolicity gives good size of stable and unstable manifolds. So if the hyperbolicity does not degenerate, then you should have an accumulation of this periodic orbit, and when they accumulate, you should observe some crossing of the stable and unstable manifold. Okay. So the question is, how can we control the size of the stable and unstable manifold of the periodic point, or more generally, you could ask them that for hyperbolic measures.
You're assuming some
theory,
compactness.
yes.
You're assuming some compactness, I suppose, right?
Yes, yeah, I didn't say, yeah, you want an accumulation of the periodic points, you're on a compact manifold. Okay, so this is my question that I would like to discuss. So I will give some examples, some example and some. So one first example is the case where. So let me come back to the Hainaut maps I have discussed before, which with Jacobian less than 1/4. This is because we have more structure for this map. And let's assume that the entropy vanishes, the topological entropy. And so in this case, there cannot be any homoclinic relation between the periodic points. And so you would like that the hyperbolicity degenerates. And so in a recent work with Enrique Pujals and Charles Tresser, we have been able to describe quite precisely the dynamics of this system. So when the entropy vanishes. So for instance, we have proved that you have a sequence of renormalization which captured most of the dynamics outside the finite step of the renormalization. What remains is essentially Morse mail. And so to understand the limit behaviors of your system, you have to go deeper and deeper inside this renormalization. And so you have to look at the limit. What you observe is a set which is an odometer. And such an odometer cannot support hyperbolic measures. And so this implies that the periodic orbits in a neighborhood have a weak hyperbolicity. And so in this case, it's possible to understand the situation. So here you have a fixed point. Around the fixed point, you have periodic orbit of first generation, let's say that rotates, and that separate a new region that are permuted, where you have a renormalization, and inside you repeat this situation. So this was one example when the entropy vanishes. So let me discuss now general case. In fact, there are counterexamples to my question. So here is a construction. So it's possible to build counterexample in finite smoothness, in arbitrarily finite smoothness. So for any CR topology, it's possible to build a diffeomorphism with infinitely many saddles whose homoclinic orbits are disjoint, are independent, whereas the hyperbolicity is uniformly bounded away from zero, and the quantity is in this way. So you look to the C1 size of your system, so you take the norm of the derivative and of the inverse of the derivative, you take the supremum, the log, and the minimal Lyapunov exponent of all the saddles is always larger than this quantity lambda over R plus something. Okay? How is this example? So it's adapted from an initial construction by Sheldon Newhouse. So you consider a fixed point, fixed saddle, with a homoclinic tangency. So let's assume it has, so you have two eigenvalues, one is lambda, you contract, and one is mu, you expand. You have a stronger contraction. than the expansion. And you have a tangency. And so when you have a tangency, you may consider a box close to the tangency point. You iterate by the dynamics. So near the saddle, it behaves like something linear. And it exits the saddle, and you will get a new box which has been stretched in one direction, contracted in another one, and then you come back because you have the tangency. The point is that since you contract more than you expand, the volume has been contracted, and so you may adjust the map so that the return, the new map has an image contained in the initial one. And doing that, you may, by CR perturbation, introduce a wave. So the box is not just linear, there is a wave. And so now you have a fixed point, and you compute what is the expansion you may observe. Since you necessarily have contraction, the volume is contracted, you observe what is the maximal expansion you may get. Okay, so take a vertical, you iterate during n time, mu to the n, and then you the box, when it returns, it is rotated by 1/4, and then because of the wave, so the vertical is horizontal, and because of the wave, it may be folded by an angle alpha. And so the new expansion now is mu to the n time the angle alpha. Okay? So you wonder what is this angle alpha you may get. You want a large angle alpha if you want to have enough expansion. And so you're constrained by the size of your perturbation. You perturb in a CR topology. The box here has a vertical size which is mu to the minus r. So the image should be contained in this box, and so the wave should not be larger than vertically than mu to the minus n. And so horizontally, you should be like mu to the minus n over r because of the CR topology. And so the angle has this form. So when you multiply the angle by mu to the n, which is the expansion during the time you're close to the saddle, what you get is an expansion like mu to the n over r, okay? Which corresponds to an exponent, a Lyapunov exponent, which is the log. So you take the log, you have a log of mu, so it's a maximal, the log of the C1 side of the diffeomorphism over r. So you come close to this bound. Okay, so in CR topology, you have counterexample. However, there are also positive results. So when even in C2 topology, assuming that you only consider saddles whose expansion and contraction are large enough, which are very, the hyperbolicity is good enough compared to the C1 side of the diffeomorphism. Okay. So in these conditions, when the minimal hyperbolicity of the saddle is larger than, so we found 15/16 times the measure of the C1 side of the diffeomorphism, then among any sequence of such saddle, you will find two that are more clinically related. How do we do that? We control the geometry of the stable and unstable manifold by a direct construction, so inspired by a classical construction of stable and unstable manifold. Okay. Okay, so this is a positive answer. So what do we expect now? We have to correct the question I've asked because they are counterexample. So let me propose this problem. We consider CR diffeomorphism in finite. So we assume that the saddles have enough hyperbolicity, so larger than the C1 side of the diffeomorphism divided by the R topology. So to fit with the counterexample just a bit larger than the number we found in the counterexample before. And so in this case, with this lower bound of the hyperbolicity, is it always that you will find two periodic orbits homoclinically related, so in the same homoclinic class? Okay. Well, I don't know how to do that, so I don't know if we could be if we could solve that soon. But maybe we can have an intermediate result. So what I propose is this one. So instead to solve it for any periodic orbits, let's try to solve it for most of the periodic points of the diffeomorphism. So here is a way to state that. So you consider all periodic orbits. You bound from below the hyperbolicity. So you consider only periodic orbits whose Lyapunov exponents are larger than lambda, some delta. And what I propose is this. So maybe among the set of periodic points, there is a large set. So the complement in the periodic points is small in some sense. So that when you consider a sequence of periodic points inside, then you will always observe homoclinic relation. So what does it mean to be small for a set? Well, either it's small because the diffeomorphism does not have many periodic points. So what you do is you look to periodic orbits whose period is less than L, and you require that the gross number is sub-exponential. So in this case, which corresponds to diffeomorphism whose entropy is 0, in fact. Or when the entropy is positive, which is the case that is interesting, in this case you ask that the growth of this set, the exponential growth of this set, is smaller than the exponential growth of the total set of periodic points. Okay. So why do we expect such a result? So shortly, that's because there are some results that exist. So the periodic points are organized into homoclinic classes. Inside one homoclinic class, the number of periodic orbits grows like the topological entropy of the class. And in this class, of course, all periodic points are homoclinically related. So you would have an answer to the question I ask if each time you avoid a small set, then all the periodic points belong only to finite number of periodic orbit, of homoclinic classes. Okay. We have proved with Jérôme Buzy and Omri Sarig that only finitely many classes have a large entropy. Okay. So if you prescribe your periodic point to be among these periodic orbits, then there's homoclinic classes, then of course you will have homoclinic relation. So what remains to study are the collection of homoclinic classes whose entropy is below some bound. So we know for each of them the growth of periodic points is less than the entropy. We don't know if for the union of them it is the case. So this is where the problem is. Okay. Okay, so I have discussed about this problem that I like because it's one way to explain how the periodic points are organized, and that's it. So thank you, and I finish with a picture. Happy birthday, ciao.
Thank you, Sylvain. Questions?
Thank you, Sylvain.
Sorry?
I think Charles was saying something.
I just said thank you.
Well, this poses a question.
Yes.
What percentage of your life have you had a beard?
Say
because
again?
in the picture, Charles doesn't have a beard, and it made me think almost every picture I've seen of you doesn't have a beard. So is that a well-posed question?
It's not a question for me.
Oh, no, it's not for you, it's for Charles.
Yeah.
Well, your beard, I think you've always had a beard, right? And I think I've only shaved my beard for about a month out of the last 40 years.
I would say probably 10% no beard.
Oh, really? Uh-huh.
Yeah. Don't know why.
It feels like it was quite a stretch. I feel like there was quite a period of time without a beard, actually.
But the many time before you with a beard.
No, I understand. So you had a beard when I was your student, but if you wait recent years more heavily.
Okay, all right, there.
Uh-huh.
All right, Marie-Claude, please.
Yes, Sylvain, is your question in dimension 2, or are there some question for higher dimension?
Yeah, I think to this question in dimension 2. I tried this question in dimension 2. I think you can ask it in any dimension.
Okay, thank you.
Any more questions? Comments? Well, if not, let's thank Sylvain again.
Thank you.
Now we have a little bit of time until next talk, I think. We'll start at 11, right?
Right.
So, okay, so it's like 9 minutes.
Right.
Actually, I have a question, Sylvain.
Yes.
What is the importance of the B less than 1/4 in the Hainan?
Aha. So that's because we use a result from complex analysis, so Wiemann's theorem, which give this property. So this property that for any invariant measure, let's say not a sink, the stable manifold escapes. Okay, both branches of the stable manifold escapes. But in fact, this is a result about in complex geometry. So you look to stable manifold, it's a complex disk, and you project the complex disk to one coordinate, and then you get an entire function, and you look how it behaves at infinity. And this is what Wiemann's theorem describes. Under some condition, the map, and so this condition can be satisfied when you look to when you compare the Lyapunov exponent with the degree, and for that the condition you get gives you B less than 1/4. Maybe it's true above 1/4, but you get immediately this condition.
Thank you.
And that has been used by Lubitsch and Dujardin, for instance, already in the complex side.
Yeah. Is there a renormalization general type of renormalization theory for these two-dimensional dissipative maps. You did it in the case of zero entropy or the exponent goes down. But in general, when you have this wave picture that you had, do you have a way of sort of blowing up near there, analogous to like the one-dimensional situation that Ubich and others used, that can give you more control on the dynamics?
Yeah, exactly. So it's what we are working on with Enrique. But yeah, we expect something like that. Yeah.
Okay, thank you.
If you look, Sheldon, if you look at periodic types of periodic orbits for disk homeomorphisms, then you have this kind of structure. Long time ago, we wrote with John Frank's paper on those things.
Oh, thank you, Hi, Michelle. Yeah, good to see you, by the way. So,
good to see you too.
We have to get together and sing sometime with Lan Wen, right?
Oh. Oh, we could have a birthday song now. It's still COVID. You can sing on acceptable.
Maybe afterwards, but
Oh, and by the way, Charles, happy birthday. Oh, you're muted.
yes, that's all right.
I'm now unmuted. Thank you very much, Michelle.
You're welcome.
All right, there you go. Where are you?
I'm in Indiana.
Okay, all right, okay. Your background looks very, oh, it's got a map. That's what I'm seeing. Okay, fine.
It's just the wall with the wallpaper.
Yeah, right.
Okay, cześć,
right.
Michał.
Cześć.
That was Polish.
Well, I have another appointment, but I was very happy seeing everybody. So till next time, I hope.
Yeah, nice to see you, Falkers.
See you. Bye-bye.
I think I do. So it's the YouTube. So all the recording will be available on YouTube later, no?
I think not the chat.
Not the chat.
Yeah, there.
No, because sorry, we were in class with Bryce, and so we missed all this discussion. Amy, say hi to Amy, Bryce, please.
Hello. Oh, hi,
Hello.
Bryce. How you doing? I was wondering who is this guy standing over Enrique's shoulder.
This mysterious masked man.
Bodyguard. Yeah, we were in the class and we were missing. But apparently everybody is very excited.
Everybody's very excited.
Well, he's very excited. Bryce was commenting that everybody is very happy with your class, Michael.
Oh, cool.
Yeah.
Good.
You have the class now? Yeah,
So Mo, do you have slides that you're going to use?
I do. You see it?
Not yet.
Not yet, no.
I see it on my screen.
Did you do share screen?
Oh, I didn't do that yet. I have to do that.
Yeah.
I have to click the green.
The green, exactly.
Where is the green? Oh,
You have to move on at the bottom on mine.
bottom.
Bottom of the screen, you should see all the stuff here when your mouse.
I see it now. Yes, I do see it. Okay. Here we go. I click share. There.
Yeah.
Oh, there it is.
Okay. Well, before we start, I want to wish Charles a happy birthday. I knew Charles from Berkeley, where he had a lot of students. If you look him up on MathSciNet or the Mathematical Genealogy Project, it'll say that we had how many students was it? It's 70 PhD students, all but 2 of whom were from Berkeley. And I wonder if you can see my face here.
Yes, we can see it.
Yes.
You see my face?
Yes.
You're in the separate panel. You're in the face.
Yeah, okay, as long as you can see it. He had 70 students, and among those students had 20 or so dependents, all but 2 of them. No?
25 at Berkeley, 2 otherwise.
25
or something like that.
Yeah.
And maybe 70 descendants, something like that.
That was what it, yeah, 20 students at Berkeley plus 28 students at Berkeley, 70 descendants, all but 2 are from Berkeley. I think 2 are from Toronto, is that right?
Yeah.
Including Pablo. But he got his PhD at Johns Hopkins University. Okay, and I know Charles, he wrote a couple of papers with him, and I knew his son by his first wife, Jenny Harrison, who's also a mathematician. They're all mathematicians. So I'm going to talk about something different from what's been talked about mostly, because quite some time ago, all these stuff about hyperbolic orbits and periodic orbits and closed orbits became too difficult to do anything interesting or new in. And what was being talked about had very little to do with applied mathematics. Surprised that the differentiability of a dynamical system should have anything to do with its long-term behavior, because he thought dynamical systems was just a way of talking about physics. So talking about physics, that's the real world. We don't have to assume anything about it. But so he was surprised at that. So he would probably have said, this has nothing to do with applied mathematics. Well, maybe it does. But I want to talk about a different way of thinking about dynamical systems. Instead of thinking about individual orbits and points and perturbations of a system as being something useful, I want to think about large sets of points in the phase space. So X will be a connected open set in Euclidean space, and I'll talk about I'm given a map, T for X into X, you ask what it does to sets of points. And so, for example, in ergodic theory, you don't pay much attention to individual points. And this is more in the spirit of that, although I won't talk at all about ergodic things. So I want to contrast 2 different kinds of mathematics: monotone systems and chaotic systems. Monotone systems are systems that preserve a partial order on the state space. And I'll only consider nice partial orders, which preserve the partial order defined by a nice convex cone in Euclidean space, E, with non-empty interior and which contains no straight lines, so called a pointed cone. And for example, you can look at the set of vectors which have non-negative coordinates. That's a typical cone, but it could be a ice cream cone or something else. And then you get an order, or technically a partial order, by saying x, point x is less than the point y if the difference between them, if y minus x is in cone. So in other words, you have to get from x to y, you have to move in a direction which is in the cone, which you think of as a positive direction. So that's a that's a partial order, x. And a map T from x to x, which I talked about up here, is called monotone if it preserves this order. That is, if x precedes y, then T of x precedes T of y. It's called a monotone map. For example, an increasing map on a straight line preserves the obvious order, and this generalizes that. So this is a very useful property of a map. It's sort of crude. It's about what it does in terms of this order, not in terms of individual coordinates so much. So such maps are very common in many fields of applied. A flow is monotone if the individual elements for positive time are monotone maps. So a flow is a collection. A flow is technically a homomorphism phi from the group of real numbers to the homomorphism group of x with some obvious continuity properties. So a flow is monotone if all the elements phi of t, all the maps for t positive are monotone. And a similar definition for strongly monotone. A map is strongly monotone if x precedes y implies some neighborhood of x. The image of some neighborhood of x precedes the image of some neighborhood of y. That is, all the points in T of u precede all the points in T of v. That's called strongly monotone. And there are many applied situations where this behavior is normal. For example, in the gonorrhea epidemic, the more people who are infected, the more people will get infected. And so that infections tend to increase. It also, in many cases, one has this property. In many cases in functional analysis, for example, parabolic partial differential equations and the elliptic partial differential equations, there are maximum principles which can be interpreted as saying that certain maps are monotone or strongly monotone. So they're quite common. But none of the talks we heard today are about such maps, although these are quite common. And the point of monotone dynamics is that it can be proved quite rigorously that they have very simple long-term behavior. And at the end of the paper, there are references which indicate this. I'll put these notes on archive eventually. I haven't done it yet, but you can find them there so you can see the references. Okay, so those are monotone maps. So two recent results of this kind. This should have been theorem 1. Bas, Lemons, and others proved that if a monotone homeomorphism is densely periodic, which means periodic points are dense in the state space, then it's globally periodic, which means the whole map is periodic. So, and then I generalized that, proved the same thing for a flow. If a monotone flow is densely periodic, it's globally periodic. And once something's globally periodic, you're just iterating a single.
Recording in progress.
The recording is in progress. Okay, so.
Mo, can I ask a question since the recording? So what is the structure that you're assuming on this space K, I mean, more or less?
K is a cone and you put it in
No,
a nice
sorry,
cone.
the space X.
X, okay, I said X is, I'm taking X to be a connected open set in a Euclidean space. What I'm saying hold a lot of things hold much more general sets and much more general partial orderings, but this is the simplest case. So for example, an example of a monotone map is a linear map where all the elements of the matrix defining it are positive. That's sort of obviously monotone. And a flow will be monotone, linear flow will be monotone if it's defined by the matrix X whose off-diagonal terms are all positive, or at least non-negative, and so some irreducibility. So these are very common in some fields of applied mathematics, especially in looking at living systems. Okay, so this is what you can do with monotonicity to prove things like this. Notice it doesn't say anything about any particular individual point in the hypothesis. In fact, it doesn't say anything about individual points at all or orbits of points. It says something about relations between orbits of points. But none of the fine questions about there's no questions of eigenvalues here. Although monotonicity has an effect on eigenvalues, they're not in the hypotheses. Okay. The other kind of dynamics I want to talk about is I say it is chaotic dynamics. So what does chaos mean? Well, a paper by Lee and York has in its title, period 3 implies chaos, which means for a map of the interval into itself, if some point is period 3, then there'll be points of many, many periods, maybe all arbitrarily. It's been used word chaos has been used in many ways, but Bob Devaney, who was a student at Berkeley, wrote down 3 axioms defining a continuous map as chaotic. The most important one is this one, sensitivity to initial conditions. It says there's some positive number delta such that any 2 points are driven apart by a distance at least delta under iteration of the map. There is a point in the orbit of x and a point in the forward orbit of x and forward orbit of y that are at least delta apart. So 2 points don't stay arbitrarily close together, which means there can't be an attracting fixed point, a stable fixed point. So that's the most important condition. And 2 other conditions are periodic points are dense, every non-empty open set in, this should say X, not Y. I don't know why it says Y. Read that as X. Contains a periodic point and what's called topological transitivity. Some orbit is dense in the state space. Now, it's amazing, but it's been proved by several people that sensitivity to initial conditions implies both of these conditions. So that's the most important condition. And a lot of work has gone into finding differential equations that whose flow, T map of a flow satisfies this. And I'll add an extra one that A is the set A, the set in which this map is supposed to be chaotic is not just a finite set. That's not very interesting. And okay, there are many places where you can find references. I found a book by Strogatz and paper by Tui and Devaney, especially Lee. I'll show these references later. Now, the important thing about chaotic dynamical systems is that unlike monotone systems, accurate long-term predictions of what happens to orbits is impossible. You can make a prediction, but you can't say it's not going to be very accurate. And I'll explain a little what that means. This was discovered by not a pure mathematician, but a meteorologist, Ed Lorenz, in a 1963 article called Deterministic Non-Periodic Flow, which was published in the Meteorological Journal. So he took the standard equations for fluid flow and simplified them grossly and ended up looking at just three coordinates. He ended up with these three differential equations. So there's only one nonlinearity, it's a quadratic linearity. And he found a disturbing. He did extensive numerical computations of solutions. So he wrote in his paper, two states differing by imperceptible amounts may eventually evolve into two considerably different states. That's the sensitivity to initial conditions. So then he said, if there's any error whatever in observing the present state, so here's the applied mathematician talking about observing the state. In any real system, such errors seem inevitable, but an acceptable prediction of an instantaneous state in the distant future may well be impossible. In other words, suppose you start from an initial state and you solve these equations, follow the solution along, and you say, well, when t equals 10 million, this will be exactly at this point because I can solve the equations. But in an actual real world system, now you can't know the state exactly. Some error is inevitable. But if the error is inevitable, the true value you start from and the slightly changed error, which is what you think you observed, will diverge by a certain amount. So you can't say very accurately how close, what the future will hold. So monoticity is very difficult to prove, and in an actual system, it's often difficult to disprove. So what it makes moral is it makes accurate long-term prediction impossible. Now, Lorenz was talking about flows. He's talking about differential equations. He's talking about following solutions of differential equations. But the way we often analyze a differential equation is looking at a Poincare map. You look at a hyperplane transverse to the orbits and take a point of the in that hyperplane, follow its orbit around, and hope that you come back to the same hyperplane again. That's called the Poincare map, which many of you are familiar with. So here's the theorem. Okay, suppose you have, in this open set in Euclidean space, you have a monotone map. You have an attractor A, or a set A, going into itself. Maps a some subset of X maps into itself. And I'm assuming that there are two relatively open, non-empty sets in U and V and A, and the order on X is such that every point of U is less than every point of V. So that's a very common situation. The conclusion is that the map restricted to A, which takes A into itself, is not topologically transitive, which means there's no dense orbit. No orbit is dense in A, so it's not chaotic. So that this simple property is not chaotic. I can guarantee that. So it's not chaotic. That's nice to know. Okay, so it was only late last night or early this morning I figured out how to prove this. So here's the proof. Let O be an orbit of a map containing some point in this set U. Choose a positive integer k such that t to the k of U is in V. If some orbit's dense, that is topologically transitive, that must happen. So then I'm assuming U is less than V, so the image of U lies in V. So U is less than that image of U, t to the k of little u, and by iterating, by monotonicity, because the map is monotone, t to the k of u will be less than t to the k of v, which is t to the k of u, and so on. So the map t to the k, the orbit is of u under t to the k is strictly increasing. So eventually it gets out of the set u because A is compact. So the orbit, which contains u, contains at most finitely many points in u, because the orbits are getting under t to the k, the orbits are jumping farther and further away. So therefore, this orbit we started with, which we assume contains a point of u, is not dense in u. So this proves no orbit is dense in the state space. And that's the end of the proof. So that's what I wanted to talk about. I'll put these list of references up here. If we can see them, there's some more, which I'll bring this down. I'll go down a little bit, not much. Okay. So there's papers by Devaney. One of the references I made to Devaney was on his book with Steve Smale and myself, but he was brought on to revise it, and the third edition, and that's where Introduction to Chaos came from. All that is due to Devaney. And see, a lot of people, maybe is John Guckenheimer here? Maybe he's here. Maybe Bob Williams is here. They wrote papers on structural stability of Lorentz attractors. Lorentz attractor is an attractor for some flow or map that's chaotic. Okay. With Hal Smith of University of Arizona, we wrote a long chapter on monotone dynamical systems and another paper reviewing monotone maps. So that's worth looking at. This is Lorentz's famous paper, Journal of Atmospheric Sciences, 1963. This is a book by Strogas that I like a lot. It's written from the point of view of applied mathematics, but it talks a lot about chaos in it. So it's worth looking at. And Tui, I don't know who Tui is, but he wrote an amazing paper, and I want to say what he proved. He proved that an equivalent definition of a chaotic system is that given any two different open sets, some periodic orbit enters both of them. It's sort of an amazing condition. That's another way you can see that such a map could not be monotone, because if one set will be bigger than the other, then you couldn't, the orbit entering both of them would have to jump back and forth and couldn't be increasing. And Tucker was the first one to prove that the Lorentz in the Lorentz system, there actually exists a chaotic attractor in this sense. And this is a paper of York and Lee, period 3 implies chaos. And I think I'm supposed to stop here. So thank you very much, and happy birthday, Charles.
Stop sharing your screen, Mo, please.
Stop sharing it. Oh, yeah. How do I do that? I clicked the red button at the top of something.
The bottom
Stop
green.
share. I see it. There we go. There's my mic.
In the meantime, does anybody have any questions for Professor Hirsch? Comments?
Well, I seem to remember a paper by Reddy and Coven from some years back, proving that if you have a map that's positively expansive, that means the positive orbit gets bigger than delta for some time, then in fact the metric is expanding.
Huh.
So you might look at that. That should
Yeah.
simplify some arguments.
Yeah, let me write that down. I find if I'm probably older than everyone at this meeting, and I find if I don't write things down, they sort of
No, good. Coven, C-O-V-E-N.
C-O-V-E-N, and Reddy?
Reddy, R-E-D-D-Y, and somebody else I don't remember.
Uh-huh. Okay, and what, you don't remember the title? Or
No, but it must have been, I don't know, around 1970 or something.
Okay, great. Thanks very much. I'll look that up. Woman and Reddy.
Nice seeing you, Mo.
Very good to see you, Mike.
Any other comments or questions? If not, let's thank Professor Hirsch again.
Thank you.
Thank you, Mo.
Thanks very much, Amy. Thanks for organizing this, Amy.
Oh, Pablo did much more than I did.
Well, thank you, Pablo, who was a student of Charles. Okay.
I'm sharing my screen. I'm trying to share my screen.
So when you press share screen.
Oh, I see whiteboard. Let's see what happens now. Not whiteboard, oh, notability.
So do you have the notability window open?
Yeah, right here.
Okay.
Now what do I do?
Are you sharing screen on your computer or on your iPad?
Oh, on the laptop. I should do it on the iPad?
Yeah, you should log in from your iPad.
How do I do that? Maybe
you could also connect your iPad to your computer.
By a cable?
By a cable or by mirroring. If you pull down on your phone, to the right, on the upper right. And then there's like something that says screen mirroring. Yeah, you press that. And then you have to do something on your computer. Does anyone remember?
Mirroring's a little more complicated and usually doesn't work. I'll just use a cable.
I think, yeah.
You have a cable?
If you just
have to get a cable.
If you click on the link that Pablo sent.
Yeah.
On your iPad, yeah. Just open your email.
I could do that.
Oh, yeah, open.
Yeah. Where's Pablo's email? Is so far down.
Yeah.
If I search for Pablo, where the hell is this?
You can just search for Amy because you asked me for the link this morning.
Oh yeah, that's right. Amy Wilkinson. No, that's Komagorov. Charles Fest.
Oh yeah. Yeah.
Okay. Join the meeting. Like this.
Yeah. Click join the meeting. Now make sure if it says sound, make sure the video is off and sound is off.
Actually, click Wi-Fi.
No audio. No audio.
No audio.
Maybe I can close it on the computer.
Also.
Well, are you there? Did you log in successfully? Oh, there's Michael's iPad. Okay, I think you're okay. Mike?
Now he closed all the audio. Okay.
Well,
no, it's okay.
Right there.
Turn on the audio on your computer.
You're fine. So now turn the audio, unmute yourself.
Yeah, on the computer. No, turn on audio on the computer. Oh boy.
Mike, we can't
No
hear
mic.
you. Unmute yourself on the computer. On the computer.
Yeah, I
There you
do
go.
that. Now, is
Good.
that okay?
Yeah.
Yep.
Except
Great.
you're getting the feedback because the sound is on and you're.
Yes,
No,
not
I
a
turned
good
the sound to
idea.
zero on the computer.
No, just
No?
start over.
Start over.
So
Yeah.
leave Zoom
Leave the Zoom on the iPad.
on the iPad.
Yeah.
Now, carefully.
Leave the Zoom.
Yeah.
Where's the leave? Leave.
Red thing on the bottom.
How's that? Is that better?
You're
No.
gone, right?
Yep.
Just leave it.
We are good. Yes. Now it's.
I'm not,
Now we're going to
okay?
start over. Yeah,
Start
now take
over.
your iPad.
All right, leave meeting. 1 second. I'm leaving the meeting. All right, here's my
I think
iPad.
you've done that.
Yes.
Now go back to my
Good.
I
email.
don't hear you now for some reason. 1 second.
Right.
Because I turned my sound off on the.
We hear you.
On the computer.
Okay.
Yeah.
Now we.
Now go back to the iPad, open the mail, click on the link. Go back to mail.
There. There. Click on the link.
Yes. Now, slowly.
Yeah.
It'll say join, right?
Okay. Good.
Yeah.
Yes.
Now, no video,
Show the-
no audio.
No audio.
No audio. Exactly.
No audio.
That's
Now we
okay.
are good.
Okay, now press share screen on the iPad in the green.
1 second. Share content.
Yep.
Yeah.
Green. Share content. Green.
Share content will be really exciting. We get all
And
your.
then do
stuff.
screen.
Green. Yeah. Zoom. Now what?
Okay, now press start share or start broadcast.
Broadcast.
Okay. Yep.
There you
Now go to notability.
Yeah. Now.
Go to notability. Swipe up or whatever. Yep. Now press the notability icon. There you go.
There you are.
It's my pleasure, and not a moment too late, to introduce our final speaker, Mike Shub, longtime collaborator of Charles, and he's going to tell us about lots of stuff.
I'm sorry about this confusion, but I'm teaching personally. So I got to my office after a year and a half of not being there, and of course the computer didn't work. So I spent a couple of days trying to fix that, and then yesterday I went to teach, and the door was locked to the classroom. So I gave up completely on City College, and I'm at home using things I don't usually use. Anyway, Charles, happy birthday, and many, many happy more birthdays and long, healthy and productive life. I met Charles in 1964, so it's already almost 60 years. And we became very good, close friends. And also we had a wonderful collaboration. I've had several wonderful collaborations in my life, and the one with Charles is as good as any. It's really been wonderful, Charles. So let me try to say something about what we did together. It was many years ago, and actually I could hope to get it back because it was so great, but he's too involved with Steve Smale. So here's what happened. We were at lunch one day, and somehow it came up the question of the ergodicity of the time one map of the geodesic flow. And I said, come on, we have enough talent at this table to solve that problem. And in fact, we did, because Matt and Charles were there, and they solved the problem. I don't remember what I had to do with that paper, but maybe it was something since we wrote it all together. But anyway, they solved the problem. They proved the ergodicity of the time one map of the geodesic flow. And along the way, they had to consider sets that had a shape which they called Julians. So after a while of processing what had been done, that's always a great thing when you finish a paper. When you finish a paper, you should always try to figure out what the paper means. And so they finished the paper, and we try to figure out over the years where it really fit inside mathematics. And we come up with some conjectures. So the conjecture is that stably ergodic diffeomorphisms are open and dense among partially hyperbolic C2 volume preserving diffeomorphisms of a compact manifold M. That's the main conjecture. As far as I know, it's the only one that survives, like stable structural stability. It's not dense. Omega stability, it's not dense. But here we got one, it's got a good chance. The conjecture has been around for, 30, 40 years, and it's still standing. And in fact, we have a suggestion for how to prove it, which is conjecture 2, that when you have this partially hyperbolic system, you can try to join points by going by paths first in the unstable, then the stable, then the unstable, the stable. You get 2 points equivalent if you can join them by such a path. And the equivalence classes are called accessibility. And our conjecture is that the accessibility of any 2 points in the manifold is an open and dense condition among C2 partially hyperbolic diffeomorphisms, volume preserving or not. So I must say that somehow in this notion of accessibility, I really found in the control theory literature, and in almost all C0 single vectors are accessible. So there's a good chance for this as well if one knows how to prove it. And the third one is that partially hyperbolic C2 volume preserving diffeomorphism. The equivalence classes are measure 0 or 1. There's no other invariant subsets. So the theme is a little hyperbolicity goes a long way. And the papers are, this last conjecture is proven with some conditions. So the conditions are, well, accessibility you have to have, and that there's some bunching on the contraction and expansion compared to the contraction and expansion in the center direction. So in fact, everything I know about that involves these bunching conditions, and in fact, the best results on the bunching conditions are due to Burns and Wilkinson. So there's still something to be done. Are the bunching conditions optimal, or can you push them down to 1? The other thing is that we isolated a dynamical condition about the Juliennes. So the Juliennes are sort of long in the center directions and usual Markov type things in the unstable and stable. And what we proved is 2 things: that the Juliennes are density basis, and that they are, the maps along the Juliennes are quasi-conform. So that means all density points were preserved. So the trouble with the Hopf argument, the Hopf argument says you get ergodicity for Anosov things because forward limits have to be constant on stable manifolds because the points get closer, and on unstable manifolds because the points get closer in the negative. And so then you can navigate between any 2 points by stable, unstable. And the thing is that the dimensions for Anosov are complementary, so that you really do hit. But here, the dimensions may not be, you're missing the center dimensions. So you really can't sort of get everywhere. So there's this problem about moving a set where you've got values around the manifold. And this Julienne quasi-conformality lets you do that. So these Juliennes are somehow dynamically defined. And so you might wonder if there are other classes of dynamically defined sets that also form density base. So that somehow you could use the structure of the dynamically defined set to approach the ergodicity of the map. So then there's this question of the accessible sets themselves. You maybe heard the morning talk by, there we go, names again.
Andy Hammerlindl.
Yeah, Hammerlindl, yeah. So he, this is repetitive, a bunch of things he said, but he also drew some pictures of what accessible sets were. And all his pictures were, they were manifolds. And that's the question, I think, are the accessible sets always manifolds? Maybe homology manifolds, it's not quite manifold. I don't have any idea how you would make another example. You start out with a curve, you start looking at curves through it. If they're not all along it, you'd expect to have some place where you get a two-dimensional little neighborhood. And then because the accessible sets are really homogeneous, if you get that somewhere, you get it everywhere. You start expecting that you'll have at least homology manifolds and manifold. So that's another favorite question. I'm just listing some of the favorite questions that I remember. I don't remember too much about the subject, actually. It's been a long time, but I do remember some of these questions and why. And then there's the question of the unique ergodicity of the strong, stable foliation. So you've got U, you've got S, you've got C, and you may have the stable ergodicity of the dynamics, but you might also have the unique ergodicity of the strong, unstable manifold foliation, which would already prove the ergodicity of the map. So this is a stronger thing. And as far as I remember, one second here. Oh yeah, here I put some references. So here, an article in the Bulletin of the AMS, 2003, there was a survey that Charles and I wrote and had an appendix by Starkov. And then the better version by Burns and Wilkinson, where they get the bunching tighter. So they get a larger class where the theorem is true. But then I remembered another one this morning, so I wrote it in here. It's not too easy to read anymore. It's unique ergodicity, and that was also by Charles and me and Starkov, and it was in discrete and continuous dynamical systems. And they were proving unique ergodicity in the context of flows on homogeneous spaces. So you take an automorphism of a group and you follow it by a left translation. And that'll be a map, and you have an invariant group for the automorphism. Sorry?
Sheldon, mute.
Off your mute. Turn your mute off. All right. So, so there is this result. I think it's mostly, in fact, I think the Hopf argument can be adapted to the homogeneous space setting and to prove this unique ergodicity and other things about hyperbolic flow. So in fact, I think one of these theorems is proven for the affine maps. You can find it in the in either one of these papers. So what are the references? So for the horocycle flow, Furstenberg proved a long time ago that the unstable manifold flow, the horocycle flow, is uniquely ergodic. Then Bowen and Marcus proved it in the axiom A context. So that's my memory about where it stands with the ergodicity of partially hyperbolic diffeomorphisms that preserve value. There's a little bit of the history that I might mention, and it goes a little bit further. It's how these concepts and definitions evolved over time. I guess Smale somehow for the horseshoe, and then for allied systems like the Tom diffeomorphism, wrote down these axioms, which are kind of ever generalize things to the infinitesimal level that way with respect to structural stability and other concepts. But then I guess he went to Moscow after some meeting in Kiev, and there was Anosov and Sinai and Arnaud, and they talked for a couple of weeks. A couple of years later, Anosov wrote this article about geodesic flows and closed Riemannian manifold. Maybe Yasha Pessin was here, I think, so he might know this history a little better. I would imagine that the Russian school was interested in this ergodicity of geodesic flow questions independently of the structural stability question that Smale probably raised when he got there. But Anosov and Sinai wrote a paper in Russian Math Surveys using the Hopf argument to prove the ergodicity of the Anosov systems. And actually, Bill Parry explained that to me in his office in Newark in 1969. But the new thing was the proof of the absolute continuity of the stable manifold foliation. So then Hirsch, Pugh, and I wrote a book on invariant manifolds. The Anosov picture, which was just about the solution curves of flows, and now we could talk about it in terms of invariant laminations of the space that were now normally, we called it normal hyperbolicity, so that the normal space actually had a hyperbolic structure. And we developed that theory, at least from the topological and structural stability point of view. Brin and Pessin, I think, probably under the influence of Katok, studied those systems from the ergodic theory point of view, and they wrote a paper about the ergodicity, but they assumed that the foliations were smooth, which they generically are not. So then Grace and Pugh and I had this first paper, and then the history went on. You can find the references in the 2003 American Math Society survey, 2003, this one here. And after that, there's a lot of work done on partial hyperbolicity, ergodicity, and various levels of smoothness. And you should consult Amy. She's the more expert. I have not been following this work the last 20 years or so. And but Amy has contributed what's known. That's another great thing about relationship with Charles is his students. He got to share his students to a great degree, Andy, and especially Amy some years back. So that's been a great collaboration and a great benefit of having collaborated with Charles all these years. So anyway, maybe I got finished quicker, but I think I've said everything I meant to. Well, I can tell you a couple of stories about the ergodicity of the timeline map of the geodesic flow and allied systems and the results on homogeneous spaces. This is some years ago. I was invited to Rutgers to give a talk in their colloquium, and I guess I talked on complexity theory. And when I got there, I was summoned to Gelfand's office. He was already somewhere in his 80s, and he sat me down. You go into the office, there was a blackboard on one wall, 3 chairs right in front of it, and his desk perpendicular to that structure. And actually reminded me a lot of getting tutored for my bar mitzvah, something like that. There was a rabbi sitting there, 3 chairs where young boys could sit and be tutored. And so he got up and he said he'd heard about my. Tell me about his work on discriminants. So he started to lecture me about discriminants, and luckily somebody came in and rescued me. And I went and gave my colloquium, and I came back after the colloquium to the tea, and there at the coffee urn there was Gelfarm standing. And so we pick up the conversation that he had in his office. And I decided, I'm saying that, I said, here's this guy, he's in his 80s. I'm going to see how good he is. So I changed topics to the ergodicity and homogeneous space. And I must say he didn't miss a beat. He picked up his 1950 papers immediately and started to lecture me about their representation theory proofs. Anyway, I'm sorry, that's some other type of story. Okay, Charles, thank you so much for all these years of collaboration and friendship, and happy birthday.
Michael, thank you. I am very touched by all these years. And I want to add something, which is you belittle your role in the GPS. If you hadn't thought of the way to ask the question, nothing would have happened with that. If you hadn't seen, this is the question to ask. That's the great thing to me about our collaboration, is you see what's true, probably home and figure out the details.
Yeah. It's great that Charles is one of the few people in the world who listens to me, but he certainly has all contributions are not entirely like that.
Well, that's how it feels to me.
Yeah, it's great.
Okay.
It's been great collaborating with you in all ways. Great.
All right. And Amy, thank you so much for organizing this. I know Pablo did the hard work, and thank you, Pablo, but you thought of it.
And had the idea. Well, okay, we thought of it together. Conversation.
Happy birthday, Charles.
Yeah.
Yeah, I thought you said
Okay,
that.
Christina.
I thought Michael was gonna sing "Happy Birthday" now.
Yeah.